Hello and welcome to our Introduction to QGIS course. My name is Ujjwal Gandhi and I'm the founder of Spatial Thoughts. I'll be your instructor for this beginner-friendly course that'll teach you everything you need to know to start using QGIS as your primary GIS. We'll be covering a variety of topics, including how to load a variety of data sets, visualize them, create maps, do data editing, georeferencing, and finally use QGIS for doing spatial analysis. This course is also suitable for complete beginners who have never used a GIS software and want to learn how to use QGIS. You'll also be learning some GIS concepts as we apply them using QGIS. If you do not have formal GIS training, I strongly recommend that you watch my practical introduction to GIS video, which I have linked in the description. That will help you understand some of the core GIS concepts around the spatial data model and coordinate reference system. This course is meant to be hands-on. That means as you're watching the video, have QGIS open and try to follow along and replicate what you're seeing on the screen. I've been using QGIS for almost 20 years, and it is a very capable and mature piece of software. I'm glad you've chosen to learn QGIS and excited to be part of your QGIS journey. I wish you all the best, and let's get started. This is the Introduction to QGIS course. We are going to learn how to use QGIS for your GIS workflows. My background, I come from a traditional GIS and remote sensing background. I learned GIS in the year 2000. That was my first introduction to spatial data and remote sensing. And I learned GIS on ArcView. ArcGIS was my commercial software that I used for doing all my work. And around 2004, 5, this is where I was finished my master's degree. I was in the US and I was looking for a job. I got hired at this startup called Keyhole, which was doing this globe viewer of satellite imagery. And as I was about to join them, they got acquired by Google. And that's how I ended up at Google. I spent most of my career at Google working on satellite imagery and GIS team. One of the things I had to do at some point was we started building the maps team. There were literally hundreds and thousands of users of QGIS across the organization, users of GIS and spatial data across the organization. And it was not sustainable or even feasible to maintain those commercial licenses across the organization. So I was responsible to migrate all our internal users to QGIS. And that's where I started working very closely with the QGIS team, started working and developing learning contents for my team, whom I was migrating, and also for the general public at this time. And since then, I've been very closely associated with the QGIS community and also worked on enhancing and helping people learn QGIS. Vigna, you can introduce yourself.
Yeah, so I have done my master's in geoinformatics, and after that, I have started working with several government private organizations. I have experience in developing plugins in QGIS, and now as a part of Spatial Thoughts team, I am working on all the different aspects where we are using different applications and different softwares of GIS.
Just want to tell you a bit about how I've used QGIS over the many years that I've used it, just to give you a glimpse of what is possible and how the software has evolved. This was a screenshot that Gary Sherman, he's the founder of the QGIS project, he had posted on Twitter. This was his kind of first version of QGIS that he had released in 2002. So it's 22 years that the software has been around. And he designed QGIS as a way to view the data that was stored in the PostGIS database. There was this really capable database that could store spatial data, but there was no way to view it. So we designed this simple viewer that can view the data from PostGIS. So the root of QGIS is actually as a database viewer. And even till date, the strength of QGIS is that it works really nicely with PostGIS. In a lot of enterprise deployments, people use PostGIS as the data store and QGIS as the viewer. Over time, the project has evolved and matured significantly. The first time I learned about QGIS was in 2006. That's where I had to find an alternative to commercial software that we're using, and we wanted to have a way for people to view data, do some simple analysis, edit data, and then push the data to our database. And I discovered that QGIS was quite capable. That there was some missing pieces, and there was literally no documentation and learning material. So that's where I started creating some learning content around that. I designed a course and tutorials for my team. Later, I asked my boss, can I just make it public so others can also use it? And they allowed it. So that's where my site QGIS tutorial was born. I've been publishing tutorials and maintaining this ever since then. And it's grown to have many tutorials. It's now also translated into many languages. So if you're teaching QGIS and you want QGIS learning material in Spanish or Italian, you can go and use this. And these are designed as labs to be taught at university, because one of the bottlenecks that people face is they want to migrate to QGIS, but then there are no ready-to-use labs. They have to design the labs for the students. So each tutorial is designed as a lab that you can use in your class. It's also great structured learning material that you can use and develop your skills. I also started developing stuff for QGIS, enhancing QGIS functionality by developing plugins using Python. I worked and published some plugins for Google for their enterprise mapping platform. Towards the end of my career at Google, I was really interested in teaching and wanted to do something on my own. So I became a certified QGIS trainer. And once I left Google in 2020, I started developing a lot more training content, more focused on different domains. We already have content for urban planning and hydrology that is available. I'm currently working on developing some content for public health, and you'll see those available as well. All the content is open source and free to access. My current interest with QGIS is to use QGIS for a lot of the remote sensing workflows, which were not possible so far. But now with the advent of new technologies like cloud optimized geotiff and this new way of working with large data set called cloud native geospatial, which is now allowing you to use QGIS to do really powerful analysis without really downloading data. So that's my current interest. I'm developing some content around that as well, and look for that content soon. A bit about QGIS. QGIS is currently the world's most popular open source GIS software. It's a very capable, very widely used software. Any guesses how many people use QGIS? Let's say, any guesses how many people used QGIS last month? Think of a number. How many users do you think use QGIS in a month? For the longest time, there was no way of knowing. The QGIS team in the early days decided that they didn't want any sort of tracking on the user side. And they were very against any kind of user tracking. So you could download the software and use it, and the QGIS team would not know that you were using it. Recent years, though, there were people really wanted to know. There were a lot of kind of interest in knowing how big is the QGIS community. So they added a privacy-safe tracking to QGIS. Again, it doesn't track any personal information. What it does is that when you open QGIS, once per day, when you open QGIS, it just sends a ping to a server and say, hey, somebody open QGIS from this location. And it just sends once per day. If you close it and open it again, it doesn't send that ping. And now we have data on who's using QGIS where, and how many users we have. Here are the current numbers. About 15 million monthly users who open QGIS in a month. About 700,000 users open QGIS on a daily basis. And this is probably an undercount, because if you are in a company and you have 10 users, you are behind a single IP, it just counts as one user. So again, the real number is probably a little larger, but again, you get a good estimate of how many people use QGIS. This is again great to get an insight in QGIS. If somebody says, oh, QGIS is not good or not popular, you can just show them these numbers. There's a nice dashboard. It's available here, analytics.qgis.org, and this shows the numbers. And it's got a lot of data on maps and about how the QGIS usage happens. You can see about 700,000 people use it every day, and on the weekend it's a bit lesser. You can see where are the users from and so on. It's also useful for the development team to say what versions people are using, what operating system they're using. And again, majority of people use it on Windows, and again, many of the people are running fairly recent version of QGIS. So again, really interesting data set about usage of QGIS. You have the raw data also available around this. If you want to do your own analysis and slice and dice it, you can get access to the database as well. So fairly large user base. It's also very mature and very stable, contrary to a lot of open source software, which were personal hobby projects or people are not very active. This is very actively developed software. There's a mature organization behind it. There's a non-profit, registered non-profit that manages the whole QGIS project. They receive a lot of funding in terms of grants and donations, and they manage and use that money to improve QGIS. QGIS itself is a full suite of software. So many of you would have just used the QGIS desktop, which is the most popular application. But QGIS also has an ecosystem of applications that allow you to take the maps that you created and publish them online. So you have software called QGIS Server and QGIS Web Client. This is also part of the QGIS open source project, where you design a map in QGIS, press a button, the map that you created goes and gets hosted on a web server, and people can interact with the map and see the map on a browser just the way you designed it. So it's a great way to use QGIS as an authoring platform and push the map out on the web. As a user, you would not install and configure the server. There are providers who run servers, which are QGIS servers. You can sign up, they have a plan that you can choose, and then you can connect your QGIS to their server and publish data. So as an organization, you can use one of those hosted mapping providers who provide services for those software. This is a great way for you to integrate QGIS, not just your analytical workflow, but also your map publishing workflows. QGIS is also available on mobile phones. These are mainly designed as data collection apps. There are two open source apps. One is called Mergent Maps and another one is QField. Both work on Android and iOS, designed to help you collect data in the field, and then the data streams into your QGIS desktop. So you can have multiple people online or offline collecting data. As a save and sync data, the data flows into your QGIS desktop environment. You can analyze it, design maps, and then you can push a button and the data goes to the web. So you have a full suite that takes the data from the field all the way to cartography to web. So QGIS has all of these components available to you. For the course, we're going to focus on the QGIS desktop application, which is the GIS application that allows you to do cartography, data analysis, and data management. Our course is divided into 4 modules. The first module will learn how to create maps. So we'll start learning QGIS by loading different kinds of data. QGIS can load all sorts of spatial data. We'll load different kinds of data and see how we can import data. How do we apply some style? How do we create different kind of symbology around that? How do we add labels to it? And then finally, how to design nice print layout and create a high quality map that you can publish it as a PDF or as a PNG image. In the second module, we'll start doing some analysis where we'll learn about joins and data normalization techniques. This is an important concept that you need to be aware of when you are creating any sort of maps or doing data analysis. We'll learn about that, and then we'll create a population density map. And we'll take some data, do some table joins, and create a map, and you'll learn how that workflow happens in QGIS. In module 3, we'll focus on these 2 concepts around georeferencing and data editing. When you have old maps, such as scanned maps, don't have coordinate systems, you want to get them into a GIS environment, or you have some existing data, you want to edit, enhance, or modify it. Those are the skills that you typically do not learn when you just start exploring QGIS on your own. So we're going to cover this in depth. So you can now get access to data which is otherwise not accessible. So you can get access to old maps, PDF maps, or have existing data sources that you can enhance. So learn those skills, and we'll solve some really interesting problems using these techniques. In the last module, we'll start doing some real-world analysis. We're going to take a problem and say, I want to figure out what's a population that lives around a certain distance from a public transport station. And we want to do this analysis for any city of the world. So we'll learn about this really amazing data set called OpenStreetMap, that you can get this open source, freely accessible mapping data, which we'll use in QGIS to do some geoprocessing and learn about how to do some analysis. And we'll get some statistics on how many people live within 1 kilometer of a public transport station in your city. Okay, let's get the data package and get your system set up. This is the course homepage, which has got everything you need for this course. This is on our OpenCourseware site, and the full link is also linked in the video description. On this page, you can find the link to get the data package and download this file, introduction to QGIS.zip. This zip file contains all the data sets that we'll be using in the class. So go ahead and download this data. Once you download it, you'll have the zip file on your computer. Here, I have saved it on my downloads folder. I'm going to go and unzip it. So we have unzipped it to a folder. Make sure you unzip the file and have all the files in the folder. Once you unzip it, you'll have this folder called Introduction to QGIS with all the data sets. And throughout the course, we'll be using these data sets. Your data package also has a solutions folder. This solutions folder contains a variety of checkpoint projects. The entire course is divided into smaller sections. At the end of each section, we'll give you a short challenge where you can practice the skills you just learned and solve a problem. You can use these checkpoint projects to catch up to that point in the workshop and then do the challenges. Let's open QGIS. You can go ahead and start your QGIS. We are using QGIS LTR version 3.34. I'm on a Mac, so my Mac version of QGIS will look slightly different if you are on Windows or Linux. But once you start QGIS, go ahead and do project and new. You'll just clear your canvas and you have a blank canvas that you can start with. Everybody may have a slightly different interface. You can customize your QGIS interface. You can turn off certain toolbars, install different plugins, etc. You want to make sure that all of you have certain toolbars and plugins that you need for this course. So first, let's do the configuration. From our course material, we have two configuration things that we need to do. First, we'll be using several toolbars from several tools from the toolbar in QGIS. You want to make sure that all of you have these enabled. So you can go to View, Toolbars, and make sure at least these toolbars are visible. You can have more than this, but at least make sure that you have the attributes toolbar, data source manager toolbar, digitizing toolbar, map navigation toolbar, plugins toolbar, project toolbar, selection toolbar available. Quick OSM you don't need. You can turn it off if you want. So you can use this view toolbars section to turn on and off certain toolbars you want. We have this available as a screenshot here. So make sure you have these toolbars enabled. You also have a toolbar management tool available by right-clicking anywhere in the toolbar. So if you have this toolbar area, if you right-click, you get these panels and toolbars, and you can use this to turn something on and off. So instead of going to the menu, you can also just right-click anywhere on this toolbar area, and it'll pop up this toolbars and panels. You can go and turn on the toolbars that you need. So make sure you have this toolbars enabled. One pro tip, if you're using QGIS a lot, all of your configuration, like we enable certain toolbars, that configuration is saved in something called a profile. So your current profile has this information that this user now has enabled this toolbar. If you say, when I'm doing certain kind of work, I'm doing digitizing work, I want all my toolbars. When I'm doing just some map making, I want the fewest toolbars. You can actually create different profiles. You can go to settings, user profiles. Everybody should have a default profile. You can always create a new profile, change your QGIS layout, and switch between those profiles. So now if you switch to maybe a simple profile where you just have no toolbars, you can use QGIS with that, and you can have those saved. So either you are multiple people are using the same computer, or you want QGIS to be configured differently for different use cases, you can have different profiles. Second, we want to install some plugins. Plugins are this third-party software that people have published that adds some functionality to QGIS. We'll be using these two plugins in this course. One is called Quick Map Services, which allow to get access to base map data from different providers, such as OpenStreetMap, and use them in your maps. We'll also use Quick OSM, which allows you to download data for spatial analysis. So let's go and install this plugin. The way you install the plugins is to go to the plugins menu, manage and install plugins. From there, you can go and search for these two plugins. I'm going to show this on my QGIS. You can go to plugin, manage and install plugins. Select the all tab. You can say Quick Map Services, no space in between. It's called Quick Map Services. So once you find this plugin, first one is a Quick Map Services. Go ahead and install this. It'll take a minute or so. And the second one we want to install is called Quick OSM. OSM stands for OpenStreetMap. These are two really useful plugins. Almost all my QGIS installs at least have those two plugins installed because I use them a lot in my work. So you can install it and have it ready. Another tip for QGIS users, one of the top complaints that you may hear from other people or your students or your colleagues is, when I start QGIS, it takes a long time to start. It takes maybe a minute or sometimes 5 minutes to start. And I hate waiting for QGIS to start up. The reason it takes QGIS long to load sometimes is when QGIS starts, it's going through all the plugins you installed and loading them one by one. So if you are frustrated with your slow QGIS start time, one tip is you can have as many plugins that you want. So I have literally 50 plugins installed, but do not enable them. So for example, you install this Quick OSM plugin. You're not using it right now, turn it off. It's there, but it's not being loaded. So next time QGIS starts, it's going to start very fast. It's going to be blazing fast when it starts because it doesn't have to load the plugins. Whenever you need it, go and enable this plugin. You don't have to download, just enable that. So keep the plugins disabled, the ones you're not using actively. They'll really improve your QGIS start time. With that, we'll get started with our first exercise for today. We're going to learn how to use QGIS to load some data, visualize it, and create an infographic like this. This is the map that we want to create. We're going to create a map of the 10 largest earthquakes that happened in the 2 decades between 2000 to 2020. We'll start with a blank canvas. We'll first get all the data that we need. So we'll need a data for the landmass of the world so we can see where everything is. We'll get data of all the earthquake faults. So these are the active faults active fault lines as a reference. Earthquakes happen near faults, so a fault serves as a good baseline to know where the earthquakes might happen. We'll load all major earthquakes that have happened in the last 20 years. All these red dots are all the major earthquakes that have happened. So we'll get data for those. And then we'll get data for the 10 largest earthquakes. And then we'll create an infographic where the map is styled so that the circles represent how bad the earthquake was. And we'll define the size of the earthquakes and the number of people that got killed in that earthquake. So we'll create this proportional circle map. We'll learn how to do this in QGIS. We'll also learn how to label our maps with callouts like this. And at the end, we'll create this nice layout where we have a map, a title, some logos, and our data sources. And this will be our first module where we'll learn how to create maps. We'll work through step by step. It's divided into 4 parts. At the end of each part, we have a checkpoint project that you can load and catch up to the point. But if you are able to keep up, try out each step as I'm doing this. I'm going to explain it, give you some time so that you can also follow along. At this point, all of you should have downloaded this intro to QGIS zip file and unzipped it to a folder, and you should have all the data here. Let's load this data one by one and see how we can get this data. First, we want to load this data of the landmass. The first data source that we are going to use comes from this dataset called Natural Earth. This is an open source project where you get really good global scale dataset. So if you're starting on a mapping project, you want some data, this is a really high quality data that you can get from here. We have downloaded a data of the landmass for the world. This is a good starting point for global maps that you can use as a base map. So let's go and load our data from there. To load any data in QGIS, you can use this button. It is next to your project button. This button is called Open Data Source Manager. Go and find this button. It's got this 3 squares with a plus icon. This icon is to load all kinds of data. Whether you're looking to load data from your computer, from the internet, from a database, this is a single dialog that will give you access to all of those functionality. Go and find this icon on your toolbar. This will be in the data source toolbar, data source manager toolbar. So make sure you have that enabled. Once we click on it, we'll get a dialog box like this. On the left-hand side, we have a panel that shows all the different types of data that you can load in QGIS. QGIS supports loading vector data, points, lines, polygons, raster data, drone data, satellite imagery, aerial imagery, mesh data. These are the climate data, such as NetCDF, GRIB, or output of your hydrological model and so on. Point cloud is LiDAR data. Delimited text is your CSV files. GeoPackage datasets. GPS, you can connect to a GPS data that you collected on a GPS device. Bunch of databases, you can read data from a bunch of enterprise databases. So if you want to connect data to your internal databases, you can use this. You can also connect to an ArcGIS server. And this is something that helps a lot of people migrate from an Esri ecosystem where you have all your data stored in the Esri ArcGIS servers, and you want to migrate to QGIS. Maybe stop using the desktop version, desktop ArcGIS. You can use QGIS to fetch data from an ArcGIS server, and that helps at least your desktop users migrate to QGIS. So you can load very different kinds of data set. We're going to load some vector data. So go and switch to the vector tab and click this button, the 3-dot button next to vector dataset, to browse to the data package. So we're going to click this browse button. So we open the data source manager, click the vector section, vector tab, and click this 3 dots. We locate the folder where we have unzipped the data. And from the data package, we're going to find this file, any for natural earth, 10 million, 1:10 million scale, land. So this is the data layer, which comes in as a shapefile. If you're new to GIS, you will be surprised to know that a shapefile is not a single file. It's a collection of files. You need at least 4 files for the file to be called a shapefile. It's an old data format, but still very widely used. So if somebody sends you a shapefile, it's not a single file. It's at least a collection of a bunch of those files with different extensions. To load this in QGIS, you just need to point to the main file, which is the .shp file. So you can go and point to the any 10 million land shapefile and click open. And once you have that here, you can click this button, add. And this is going to load this shapefile onto QGIS, and you'll see this map on your canvas. On the left side, you have a layers panel, which will show the layer that you just added. So when you load it, it may appear in blue or purple, doesn't matter. When QGIS loads it, the data comes in a specific projection. You can see at the bottom right corner that this data is in this projection coordinate system called 4326. This is lat long. That means the coordinates are stored as latitude and longitude. This is a geographic CRS, and we have the data. QGIS, if you add data in different CRS, QGIS will automatically overlay them on top of each other. So you can work with data in different CRSs together without any issues. Let's get our second piece of data. Second piece of data, this is the data set of where the earthquake faults are. The geological faults. There's a data set called GEMS, a global earthquake model. They produce a lot of hazard data related to earthquake. They produce this layer of where all the earthquake faults are, and they give you the data in different formats. We have downloaded the data from here in a GeoPackage format. GeoPackage is a modern vector data format that can hold points, lines, polygons, as well as other types of data. So this is the next layer that we want to load. So let's go and open our data source manager again. Again, we're going to load this vector data, which is the line data. So you can delete this and click on this 3 dots again next to the vector layer and go and find this data called GEM, active faults harmonized. This has all the earthquake faults saved as a line layer and saved in a GeoPackage format. A GeoPackage file can have multiple layers. This one just has one file, but it can have multiple files. If it's got multiple layers, it'll ask you which layer you want to add. Let's click open here, and I'm going to click add. Once it's done, you should see some lines appear on your screen. You'll see where all the current faults are. And if you live close to a fault, you are at high risk of an earthquake. So again, this is a great way to, the power of spatial data is that once you visualize this data, you have this rich information in multiple dimensions. Now you can say, I know there's a name of the fault, but now I can measure and see how close I am to that. The next data set we want to load is the data set of all the earthquakes that have happened. We're going to look at this data from NOAA, which is a US government agency which collects data on earthquakes. They have this amazing database called Global Significant Earthquake Database, which they have curated and collected data for all the earthquakes that have happened from 2150 BC till today. And so it's an amazing data set, along with the lat long. So you have the information of where the earthquake occurred, the epicenter of the earthquake, along with things like what is the closest town, how many people got injured, how many people got killed, and so on. We have downloaded the data for 2000 to 2020 from this database. So we have downloaded the data from this very page. And once you download, you will get a text file, and we'll now see how to import a text file into QGIS. In your data package, we have this text file, significant earthquakes 2000 to 2020.tsv. This is a file in a format called TSV, which is a tab separated values. This is a plain text file where you have different fields, and each field is separated by a tab. So the first one is year, it says year. Second one is month, and there's a tab in between. So this is a kind of data like a CSV, plain text data, but it's a structured data. We have the information about the latitude and longitude. Right? So this is the geospatial data, but it's a text file. So let's learn how to get a text file as a vector layer in QGIS. Back to our QGIS data source manager. We're going to switch to the delimited text tab. This is the tab that allows you to import CSV, TSV, or any other tabular data source into QGIS. Switch to the delimited text, browse to this file, which is called Significant Earthquakes 2000-2020.tsv. On some Windows machine, if you're not able to see this file, make sure you change it to all files. Windows, if you select it just as text file, sometimes Windows doesn't show it. So make sure you have this all files selected, and you should be able to see this TSV file. When you open this, QGIS will try to guess how to read this data as vector layer, but sometimes you have to help and configure which is your location column, which is your data column, and so on. So let's open this. Here, QGIS has detected that my data is a tab separated. So it is detected this is a tab separated. If yours is a CSV file, select that. Here, make sure you have selected tab. The UI is part of the custom delimiters. So if you open it, by default, it will be CSV. If you do custom delimiters, and it is tab. Geometry definition, it has already figured out that we have latitude and longitude column, which has got the coordinates. Remember, we say latitude and longitude, but QGIS expects the column to be X and Y coordinates. Longitude is your X coordinates, latitude is your Y coordinate. So sometimes if you load some data and it appears kind of upside down or in a skewed way, you may have made a mistake of assigning latitude as X and longitude as Y. So make sure if it's not auto-selected, make sure longitude is the X field and latitude is the Y field. The data that we have, by default, it's in EPSG 4326, it's latitude, longitude. So this is the CRS of the data. So we select EPSG 4326 in the dropdown, and that should be the default one. If everything went fine, you should see a preview in the table below. So if I see this table and I see the tabular data structure here, that means my configuration is correct. QGIS was able to interpret this data, and I'm ready to add it to my map. Click add, and you should see a bunch of points. These are all the significant earthquakes that have happened between 2000 and 2020 in the world. And you can see earthquakes are centered or close to faults. So this is the kind of visual proof that earthquakes happen near an active fault. Let's learn how to kind of view this data and select some subset of this data. Geospatial data comes in two parts. You have the location, and then you have the attributes. And they both are interlinked, and that's what gives the power of GIS, that you can not only see the data in space, but also work with the data as a tabular data. Let's open the attribute table of this layer. So for example, we have the layer here. We can right click on any layer and click this button called Open Attribute Table. This is the data table that is linked with this particular layer. So every point has an associated data that is linked with this, and you can see that. So let's click on this. It's going to open a new window which has got the table with this. You can see there are 1200 points in your map. We have different columns. We have the year in which the earthquake happened, month, day, hour, minute, second, so exact time of that. It's got some description of the location about where the earthquake happened, lat, long, magnitude. This was the intensity of the earthquake. Deaths, how many people died, how many people injured, what was the monetary damage that occurred, and so on. And you can have a bunch of other attributes. Some of them have null values, that means there's no data. Some of them have the actual values. Let's use some of these attributes and see how they're interlinked with our location data. From your toolbar here, go and find this toolbar. This is the selection toolbar. It's got a bunch of tools to select some features on a map. We have the second button here. We're going to use this option, select features by value. So this is the second button on your selection toolbar. You can click this drop down and select this tool, select features by value. This allows you to query the data from your data table and see the results on your map. So a good way to explore and understand the data. Let's open this tool. We have this form where you can use this to query. Let's say we want to know, we have the data for 20 years. We only want to see the data for earthquakes that happened in 2020. So I can say year, and I can enter 2020. It says equal to, so that means it's going to search and select all the earthquakes that happened in the year 2020. So we had used, in the selection toolbar, we had used the select features by value tool. In there, we're just entering 2020 as the year. And then you can click this button, select features. Once you select features, it says 29 features selected. So it selected 29 features. That means there were 29 earthquakes from this layer where the year was marked as 2020. Sometimes when you have large data set, you want to just quickly query and see where those points are. This is a good way to see this. You can see the selected points are turned yellow in your map. So those are kind of shown in yellow. You can also use this button, flash features, and they'll just draw your attention to those features. If I say flash features, it's going to go and flash that. So if you just doing a query and say, where is that feature that I match my query? You can do flash features and it'll just show that in your map. You can also enhance this query. You can say, I want to find all earthquakes in 2020, which were large earthquakes. So we can say, I want to also include the magnitude of the earthquake in my query. So I can say, change this to greater than 7. So any earthquake that occurred in 2020 which had magnitude greater than 7. I want to select those. So I'm going to click select button here, and it's going to match 6 features. So there were 6 earthquakes in 2020, which were larger than 7 magnitude. And again, if I want to know exactly where they were, I can use this flash features and it'll show me where those are. And you can see those on the map. This is a great way to kind of query the data, see the results on the map. And as we learned that GIS data is both map data and attribute data linked together. So the 7 features that we selected, or 6 features that we selected, those are also selected in your attribute table. So let's go and see that data in the attribute table so we can actually see more information about those. I can close this window, keep my features selected. You can see my features are still selected, and I can open my attribute table again. So right click, open attribute table. You can see my features are selected. It also shows at the top of the attribute table that I have those 6 features selected here. If I kind of go around the attribute table, I might find the row that was selected, but it's very hard for me to kind of find those 6 rows which are selected. So there is this handy tool here which says move selection to top. Go and find this button in your attribute table, which is this button with a table and an arrow. If you do this, it's going to bring those 6 selected rows to the top so you can learn more about those rows and you can look at the data. So I'm going to select this and say, now you can see all those selected rows are at the top. So these are the table gets sorted so that all the selected rows are at the top. And now you can get more information about those. And you can see these are the locations where this large earthquake happened in 2020. And you can learn more about those as well. Let's deselect all the 6 points that we have selected. There's a here on the selection toolbar, deselect all the features. So we just want to remove our current selection. So we can go and click this. It's going to remove our selection. So we don't have any selected layers. We want to create one more layer. Remember the map that we are creating? This is the map that we want to create. So we need a layer of all the faults. We have that. We have a layer of all earthquakes. We have that. We need one more layer, which is showing this 10 earthquakes, the 10 largest earthquakes. And we want to style them differently. So we want to create a new layer with just those 10 points, which are the largest earthquakes. So we're going to create that new layer from our existing layer here. Let's open the attribute table of this layer. It should be 0 selected. And we want to select the 10 largest earthquake by death count. So we're going to find the column, which is the total death. So there's a column here, total deaths. If I click on this column header, it's going to sort this table in ascending order. You can see that all the nulls are at the top, then the lower number will be first and the highest number will be at the bottom. If I click this column header again, it's going to sort it in a descending order. So the highest value will be at the top and it is sorted in descending order. So open the attribute table, go and find this column, total deaths, and click twice so it's sorted in the descending order. And we're going to just select the first 10 rows. So I'm going to select the row number 1. I can select it and then hold my shift key and select the row number 10. This will select all the rows in my table. So we sorted the table by death. So we have the largest earthquakes at the top. We clicked on the first row, it selects the first row, hold the shift key and click on the row number 10. Select the 10 largest earthquake. It should say 10 here, selected 10. And we want to take it out and save it as a separate layer so that we can style it differently. So in your main QGIS window, we have the layer here. We have selected 10 features. We want to save them as a new layer. So I'm going to right click, export, save selected features as. This will allow me to take whatever I've selected, either on the map or the attribute table. I'm going to take that and save it as its own new layer. Right click the layer, export, make sure you select the save selected features as. That's the second option. It's going to bring us to this dialog. What format we want to save? QGIS uses GeoPackage as the default data storage format. It's also a great open source data formats, quite interoperable across many different software. And also it's a modern data format that supports all different kinds of data sets. So it's a preferred data format for data management. Unless otherwise you have a strong opinion, do not use shapefiles for data storage. It's a lossy format. You lose some data as you save the data to shapefile. Store it as GeoPackage. You can always export it to shapefiles for your clients or for other colleagues. But for storing data, GeoPackage is the preferred format. Let's click this 3 dot next to the file name. You can go to your data package. and save. The file name is large earthquakes. So just name the file as large earthquakes. As you save, since geo packages can have multiple layers, we're going to add the layer name as well, large earthquakes. You're going to keep the same CS. You can also do reprojections here. If you want to save the data in a different projection, you can choose that here. Rest everything will remain as default, no changes. Once you click save, you'll just overwrite the file. Once you save it, you'll have a new file and a new layer. You can see now there are this 10 points, which has the largest earthquake selected as its own layer. Do not worry if you could not keep up. I'll show you how to catch up to this point in just a second. Once we've done the work, we want to save the work so that we can come back to this point later on. Let's go and save our work. You can go to project and save. QGIS has the concept of a project. A project is a collection of data layers and its configuration that you can store as a file. So when you open the file, QGIS will go and find those layers on your file system, load it, and style them as you had saved. So the project file will save the layers you loaded, how you styled it, where you are looking at in the map, and so on. So it'll kind of recreate this, what you're looking at in the screen, by saving that as a file. So let's save this. It'll save this as QGZ file. We can just say earthquakes. Just save the project file as earthquakes. And we have this QGZ file. Now this file doesn't have the data. It is just a pointer to the data. So if you want to send somebody this project, send them the project along with the data layers, and then only they can see what you've done. So a project is simply the collection and the styles that you have configured for your data layers. If you want to catch up to this point, you can go and load a project that is in the solutions folder called Earthquake Checkpoint 1. So I'm going to show you how to do this. In case you have done everything up to this point, you can keep your project. But if you want to catch up, you have a pre-configured project that does this kind of work. You can go to project, open, go to in your data package, there is a solutions folder. Inside the solutions folder, go and find this project, earthquake checkpoint1.qgz. When you open this, your screen will look like this. This is everything that we have done so far in the course. We have our land layer, the faults layer, the significant earthquakes layer, and the subset of the 10 largest layers. All of them, we have saved it, and now you can continue and do the challenge based on this. The solutions folder is in project, open, in the solutions folder, earthquake checkpoint 1. That's a project that we want. Recommended practice is to put your data and the project file in the same folder. That means if you zip it and send it to somebody and they unzip it, they can find the file. The default structure is relative paths. So when you say I have a layer, it is relative to where the project file is. And that's recommended for most practices. If you go to project settings, you can change it to absolute path. But again, only if you need to. The default is a relative path. So if you have a folder data outside the folder, that is a project file. And if you replicate the structure elsewhere, the project will just say, I am looking for this layer in the data folder inside of this folder. And that's how it finds it. We are done with the first section. We have a fun challenge for you to navigate and work with the attribute table. There's a popular term in GIS called null island. If you heard of it, great. If you've not heard of it, that's totally fine as well. It's a fictional place. This term is coined by geographers who have the data lost and ends up in the wrong place. So many times when you have data which has wrong coordinates or null coordinates, often puts them at this coordinate 0, 0, where x is 0, y is 0. It's an intersection of prime meridian and equator. And sometimes you load the data and your data is not there. And you say, my data is lost. It's at some west coast of Africa. And that's where the null island is. And this is a term that refers to this location where your null coordinates end up. It's a bit of a geographic trivia. You can look up the Wikipedia page for null island. This is the location 0, 0 on WGS84 coordinate system where the lat and non 0. And again, you have a bunch of stickers and some articles. People design stickers and t-shirts around null island. So now you know what null island is. It's also a useful thing where sometimes you have working with geographic data, you want to filter out data that falls here because that's the null coordinates or wrong coordinates. And exercise is to find this null island in your data set. Vigna, let's explain the exercise.
Yeah. So for this challenge, you have your any 10-meter land layer. So you have the land layer where you have these polygons, and you need to find a null island and zoom to that feature. So you can just go to the attribute table of the layer, and you will see a feature of the attribute null island. And as soon as you find it, you can just select it, and you can click the icon for zoom to the map, and you will just see that feature highlighted, and you will be zoomed to that particular portion.
And the idea is you have that feature that comes with a data set. This helps you find where your lost data ends up. So go and find the feature on the map and see if you can navigate your attribute table along with your map. We're going to now start from the checkpoint 1 project. We have so far learned how to load different kinds of data set. We'll now learn how to style the data to create the final infographic that we want. This is the map that we want to create. So we'll learn how to style different layers. We'll first style our base map into a light gray shade. So all the polygons that represent the landmass will be in light gray. We'll style our earthquake fault lines in a thin line. And then the main thing we want to learn is how to take this layer of 10 large earthquakes and apply a proportional circle symbology, where the circles represent how large the earthquake was. So let's go back to QGIS and start working on our next section. So now we're going to work on section 1.2 to apply the symbology. QGIS has many cartographic options. As far as symbology is concerned, it has gone far beyond what the competition has to offer, and you can apply all sorts of symbology and create really beautiful maps. We'll explore some of the symbology options that QGIS has to offer. All of the symbology options are available in a place called Layer Styling Panel. If you are a long-time QGIS user, you might have used this dialog. If you right-click Properties and go to Symbology, it allows you to do the same thing, but this is an old way of doing things. The modern way to apply style in QGIS is to use this layer styling panel. So let's select this layer first, the natural earth layer with the landmass, and click this paintbrush icon in the layers panel. So here you have this paintbrush icon, click on it, and open this panel on the right-hand side of QGIS. This is called the layer styling panel. It is an interactive panel where you can apply some symbology and see the result of your change in settings immediately on the map. And this is the preferred way to do any kind of styling in QGIS. So first step you want to do is we have this background continents. We want to change it to a light gray color. We have different kind of symbology options. We have single symbol, categorized, graduated, etc. We'll keep that single symbol. We want to apply the same style to all the features. That's what single symbol means. We'll select this option, simple fill. Within each type of symbology, you have different symbol types. You can have pattern fill, hatch fill, and so on. We'll keep the simple fill. We just want a simple solid color. Well, let's change the fill color. We can click this drop down and we'll bring up a color selector. Go and select a light gray color. You can use the color wheel here or the color option from here. And you can see as I'm changing the color, I can see the map change immediately. And this is super helpful when you're designing maps. You don't want to go back and forth between your settings and go and see the result. So let's select a nice gray color. And once you're happy with it, you can click somewhere out. We have our symbology. We also will change the stroke color. We'll just remove the stroke color. We have this black color outline to each polygon. Let's just remove that outline as well. So from the stroke color, we can choose this option, transparent stroke. So we have a color fill, and then for stroke, click the down arrow, and at the top, there's an option, transparent stroke. And so we have styled this layer, a basic background map, just to help us orient where things are. Let's continue styling. We want to now style the line layer, which is the faults layer. So select that, and once you select it, the symbology section will update automatically. Here we want to, again, use a single symbol. All the lines are the same color. Simple line, click on the simple line, which will give you more options. You can go and choose and pick a color, which maybe it's a brown color. Choose a dark brown color if you want. Feel free to choose a color that suits your taste. Map making is part science, part art. So use your artistic sense and pick a color that makes sense to you. Stroke width is, here is how thick the lines are. We're going to change it to 0.1. So we can adjust how thick the lines are. And this is just make it a little smaller. In all of this are background layers. The hero of a map is going to be those 10 largest earthquake. That's a theme of the map. So rest everything should just be in muted colors and should not distract the reader of the map. It should just help them understand where things are. But apart from that, we don't want it to be in simple colors and in a smaller size. Next, we want to style the point layer. So select this point layer. Here we have the simple marker. So click on the simple marker. Just have a round marker here, that's fine. We want to adjust the size of it. So right now, again, these are just serve as a background reference layer. This is not something that we want to highlight attention to. So we can reduce the size, maybe make it 0.5 or 0.7, and play around with the size and see which makes sense. Fill color, a red color should be fine. And here the stroke color, you can see even though we've chosen red, it appears a little dark because we have a stroke. You can make it a transparent stroke or choose a white color as a stroke. So whichever makes sense. And here the stroke width, you can make it very small. So I'm going to make 0.1 as the stroke width. So you can see now we have this really small, tiny icons, which are in red color with a white outline. It shows where the earthquakes are, but again, it shows where where there are more earthquakes and less earthquakes. But again, that's the point of it. So here the changes we made was change the size, change the stroke color to white, and then change the stroke color to. Next, we're going to learn how to symbolize this 10 large earthquake points so that the size of the marker is proportional to the casualty numbers. So if an earthquake had significant damage or had a huge fatality, we want to make it appear in a larger symbol, and the one that had lower fatality would be in a smaller circle. This is called a proportion circle map. I will learn how to create that in QGIS. Let's style this large earthquake layer. Select that, click on simple marker. Here we have the size of the symbol, and we can do, if you make it 10, everything becomes 10. If you make it 5, everything becomes 5. What we instead want to do is have this size be dynamic. The size should be proportional to some value from the field. Whenever you have this kind of need where you want to use the data from your attribute table to style your layer, you will see this option next to most of the options in QGIS. There's this button which says data defined override. That means you can override the value of that particular setting using some data. So let's use this. So next to the size, I'm going to click this down arrow and click assistant. The assistant will figure out how you can use the range of values in certain data columns and apply them to create this different size of symbols. So we're now in large earthquake layer, click on simple marker. Next to size, click on the data defined override and click assistant. Let me explain this dialog and you can try this out. There are two parts of this dialog, input and output. So where should your values come from? What should be the size of circle proportional to? We'll look at some data. So we want to use this total deaths column as our input. That's where the sizes should come from. We can click this button to auto load the values. So it says this column contains the value from 4,000 all the way up to 316,000. So that's a range of values. And we can say, depending on this value, you can assign some size. So right now it is assigned the size 1 to 10. That means if the deaths were 4340, the symbol size is 1. If that were 316,000, the size is 10. And you can already see the different size of circles here. We can adjust this. We can say, I want to change this from 5,000 to 500,000. So this says 5,000 and below should be this size, 500,000 above should be this size. Values in between should be created using the method that we specify here. So any data point where the value is 5,000 will be appearing in size 1. Any data point which is 500,000 will be in size 10. In between, we can apply some scaling. What method should we use? You might say size of the circle, the area of the circle should be proportional to the number of deaths. So if you want that, you can use this method surface, where if the one point had a value of 100, another point had value 200, the area of those two circles would be double. So if you had a point with 100 deaths and area A, the one with 200 value will be twice of A. So twice the size of an area. What research has found is when you have a map like this, humans are terrible at interpreting areas. So when you show this map to somebody and say, tell me if this circle was 100,000, how much is this? And humans often will say, oh, this is 150,000, where in reality is actually 200,000. So humans are very bad at interpreting scale in terms of area. So the default method that QGIS uses is this method called Flannery. Flannery is a method that was invented by a researcher named James Flannery, who did this research on human perception of symbols. And he found that humans underestimate a lot of the symbol sizes. So he adjusted the proportion so that the sizes are more in line with what humans perceive. In a course material, we have linked to an article which explains this method a bit more. And the idea is, on the left-hand side is your regular scaling. If you just use the area-based scaling. If you use Flannery, you have symbols appear a little larger than the actual scale. And this is in line with how humans perceive. So that's a default method that QGIS uses to assign proportional circles. If you want to use absolute scaling, use the surface method, which is proportional to the area. Read this article and see if this symbology is appropriate for the map that you're creating. There are obviously critics to this method, and there are obviously supporters of this method. But again, you have a choice on which one to use. We'll stick with Flannery for here, which is the default. The important thing, advice for me, is whenever you use this kind of symbology, always give a legend to people on the map so they can interpret visually. Here, right now, we don't have a legend. We're going to add it shortly, where we don't know what the size has been. Give a way for people to interpret it. That's more important. How you scale your values is secondary. You can also play around with this and say some values are small. So I'm going to go from minimum size 3 for 5,000 all the way to 500,000 for size 10. So we've done our configuration. Click back to go back to the previous dialog. There's a next to symbol size, there's this arrow. I'm going to go back. When you come back here, you can see this data-defined override has turned yellow. That means for this particular field, there's an override that is in place. So the size is not 5, it's been actively changed by this data-defined override. Let's change some of the styling options here. We're going to change the fill color to some shade of red. So you can change this to a red color. You notice that when we change this to a red color, all the stuff that is behind this, all the other earthquakes that occurred in the same region, they are getting hidden. We don't see where they are. So it'll be useful to not have a solid color, but a semi-transparent color. So in your color wheel here, you can drag this value somewhere in the middle. This adjusts the transparency for the layer. So as I come here, you can see my fill has become transparent. So I can see the points behind it. And this is a really nice visually way to say, here is a circle, but there's something behind it. So you can change the transparency a bit so that you're not fully transparent, fully opaque there. And we'll change the stroke color from black to white. So now we have styled this 10 earthquake points in a proportional circle symbology using the data-defined override. The size of circle now represents the fatality at each earthquake caused. When we create a print layout from this and have a map, it'll look like this, but there's no way for the user to know what does this different sizes mean. What are you showing on the map? So it'll be important to show a legend. So let's show the legend for our map here. To add a legend to this, we're going to click on the marker option here. So we were here, click on the marker. And here at the top, at the bottom, we have the advanced section. And we have this option, data defined size legend. This will create a legend that will use the data-defined symbology that we have used here. It's a bit hard to find. So if we are in simple marker, we did all the configuration. Go up one level to the marker, and under the advanced section, select the data-defined size legend. Here, we can have a legend like this. So it will give us the size of different circles and along with the numbers. Or you can have this collapsed legend. This is a much nicer way to represent this, where you have the circles which are kind of collapsed and you have the different levels that are displayed there. So let's use a collapsed legend. And instead of it choosing the values from 100,000 to 500,000, let's choose our own range of values based on the knowledge of our data set. So I'm going to select this box, manual size classes. And we're going to have 3 circles, 500, 5,000, 50,000 and 500,000. So these are 3 ranges of values we want to show that, if the value was 5,000, this is the size of the circle, 50,000, this is the size of the circle, and lastly, the 500,000, this would be the circle. So I'm going to click and add 5,000 plus on the one 50,000 and lastly 500,000. And you can see I have this nice legend now, which shows me that the different sizes of the circles have this value attached to them. And you'll see the legend change on our map here. This legend will also be added to the final map when we create a layout, so that people can know that when they're looking at the size and say, okay, this must be, it's a very large, this must be close to 5,000. This is kind of smaller size, this must be around 100,000 and so on. So it gives people a way to interpret the data on the map. Done. Go and save your work. You're done with the part 2 of symbology, and we'll do a challenge. Before we do the challenge, if you want to catch up to this point, you can open the earthquake checkpoint 2 project. This will have all the work that we've done so far of styling. For the challenge, we want to explore a new kind of symbology where we can apply some effects to your symbols. A very popular effect that people want to apply is do a drop shadow or have a glowing effect to each of the symbol. These are called live layer effects, and you can now use this in QGIS to apply a different kind of effects to each of your symbol. Let's explore how to do this in QGIS.
Yeah, so for the challenge, we want to have some effects on the marker that we have. The circles are the markers, and we want to have some more effects for that. And you can just explore this under layer rendering and enable draw effects. And you will see that the star button will be enabled. You can go there and try some effect for your marker. After that, you can take a screenshot and share it with me. So try to follow the instruction. We have the tools highlighted here.
One thing to try is a drop shadow. When you have certain feature that you want to highlight, and when you want to pop it out of the map, it gives this really nice effect where it shows that these are the features that you want to highlight. You can add a drop shadow to it. So drop shadow works really well, but do explore other features. Each style also has multiple settings. See which one works best for you. We're going to continue. We'll now learn how to apply the labels to this map and create a map that is ready for publication. We're going to start from the last place. If you want to catch up to this point and continue with the class, please load the earthquakes checkpoint 2 and go to project, open in the solutions folder, you have the earthquake checkpoint 2, and we're going to continue the work from here. We now work on the next section, 1.3, where we'll learn how to apply the labels and with the callouts to show more information about those 10 large earthquakes. Before we start and apply with our labels, we are creating a global map. We need to figure out what's the right projection to display this data. By default, the data comes in the CRS 4326, which is latitude, longitude. This is a projection that is not suited for visualization. It's a good format, good projection to store the data, but when you're visualizing the data, it doesn't display any of the factors correctly. All the contents appearing wrong size, the distances are incorrect, and so on. So this is not a good map when you want to show the globe for data on a globe. Here, the main problem is all the continents do not appear in the correct sizes. Africa is much larger than, for example, US, but doesn't appear, so everything is distorted. So if you are doing global maps, you should choose an equal area projection. Equal area projection preserves relative area of the continents, so that ideally you would display something on a globe, but we cannot do this on a globe, so that we want to do it on a flat surface. The closest you could represent the actual sizes is by using an equal area projection. Till recently, we didn't have a good choice of a global equal area projection that both preserve the areas, plus it looked good. Recently, there's been a development of a new projection called Equal Earth. You see the map behind me. That map is a global map in an equal Earth projection. This is a modern projection that was recently released. You can learn more about this projection on this website, equalearth.com. This projection was kind of an adaptation of the very popular Robinson projection, which was used by National Geographic. And it's a projection that is an equal area projection. That means the relative sizes of different continents are correct. So you can have a true depiction of the sizes of the continents. Plus, it has got this look, which looks fairly nice. It has got this curved edges, which gives the feeling that this Earth is actually spherical map. It's not a flat map. And it's a really nice projection to be used for global maps. NASA has adopted this as their official projection. If you see any map from NASA, you'll see that it will be in equal Earth projection. Also for you, if you're creating any sort of global map, make sure you use this map. This is much better than just sticking to the default 4326, or even worse, using a Mercator projection, which heavily distorts areas as you go away from the equator. Also, you can come here and download a nice map. If you want to have a nice wall map for you, they have a free map that you can download as a high quality graphic and print it. That's what I did for the map that you see behind me. This projection is available in QGIS and many other software as well. So let's change our map to show this data in an equal Earth projection. So we can go to the project menu, and from the project menu, we'll go to the CRS, go to the properties. So go to project and properties. We're going to change the CRS of the project. That means every data that we add to the project or has been added to the project will be reprojected on the fly for visualization to that particular CRS. We go to the properties. Here we have different sections. We go to the CRS section. And from the CRS selector, we'll go and find the equal Earth projection. Search for the code 8857. Different projections have different code. There are EPSG code. These are the most popular way to assign some numbers to a projection, so you can quickly find them. 8857 is the EPSG code for equal Earth. There are different versions of equal Earth where you have the central meridian at different places, but we're going to keep it at the Greenwich. So that is the 0 longitude is our center of the map. So go and find this projection 8857. If you do not see it here, it may be collapsed here. So you may have to expand this projected equal Earth, and then you'll find this here. So go and pick this one as the CRS for a project. As you do this, you'll see your QGIS canvas update, and all your layers are now reprojected on the fly to this projection. They've not changed the coordinate system, the data layers, it's just they are loaded and shown in this equal Earth projection. Now you can see the continents in the true sizes, and you can see the distribution of the earthquakes on the global level. After you take this class, I do not want to see any global maps from you in 4326 or Mercator projection. If you don't have another option, please choose equal Earth. That's a really great choice for global maps, and you'll always have a map that looks good, also displays the correct information. Let's add some labels. Going back to our course, we want to create some labels on the map that show some more information about those 10 largest earthquakes. We want to display the name of the place where the earthquake happened. So it says China, Sichuan province. We also want to display the actual count of fatalities on the map so that we can have this. We want to have those labels placed so that they don't interfere with the map. So we'll arrange them in a way that's outside of our map area. And we also have this call out so you can kind of see which label is linked to which data point. So let's go and step by step learn how to create these labels. Labels are also part of the layer styling panel. So let's open the layer styling panel. Here, we've been doing symbology using this paintbrush tab. Switch to the second tab, which says ABC. This is your labels tab. Let's change it to single labels. So we apply one label, and the label value comes from some column. We have different columns we can use. Let's change it to location name. And now you see the labels next to each of the point, which says the location name that is in your data table, which is now used to display the label. Few problems with this one, it's very long text, not very nice to look at. We also want to display some other information, so we don't have a field that has all the information. So we can now learn how to use something called expressions in QGIS, which are similar to functions that you may have used in Excel to create some new data based on other values. We can apply some functions, change the format of the data, combine it with other column values, and create a text that we can use that as labels. In many places in QGIS, you'll see this symbol. This is your expression symbol. That means instead of using the location, the label from this field, we can construct a new value that can be used for each of the field. Let's click on this expression button. This brings up the expression builder. We'll be using this quite a bit. So let me just give you a brief overview of what this dialog looks like. Here is where you write your formula. This is similar to your Excel formula. Here we have all the different functions that you can use. So if I expand this, these are the different functions that you can run on different data set. We also have access to the fields, all the field values that are there for your attribute table. In the expression engine, whenever you have any text with the double quotes, the double quotes means the value of this should be replaced with the value from the column named location name. So double quotes refer to columns. So if I want to say my name should come, I want to have a label with the magnitude. So if I click this from the fields and values, double click, it'll be added with double quotes magnitude. That means whatever the value from the magnitude column, that'll be used here. Default, we have the location name. You can do a few things. One is you can run some functions to change the text here. Let's say we have this text in all caps and we want to change it. So if I want to change the case to it, so we have functions, say lower, converts a string to lowercase letters. You can say I want lowercase letters, or we have a title case. This is more appropriate for a label like this. So this is like a function. So we have a function, open parenthesis, close parenthesis, and the value that we want to use. So we can run the function on this column and say, I want to change it to title case, title, and then we have the value. And you can see the preview of the output at the bottom. You can see I have the text in a kind of title case appears at the bottom. So I was able to change the value dynamically. It didn't go and change in the data table, just taking the value and constructing this new value based on the function that we ran. An example of how to use the function, we can also combine different fields. So I can say I want to display both location name and the total depth. I want to have two different values here. So I want to have two different values. I have the total deaths, which is the number of fatalities, and I have location name. I want to construct and combine them together into a single field. To combine two values, we can use this operator, string concatenation. At the bottom, you see these two pipes. If I put two pipes in the middle of this, you can see it has got the location along with the second value, the number of deaths. Combine both of this into a single value. We can also add a static text to it. I say, I want to add some text to it. So I can say, combine this, but also add this text. That's so now this says location name, add this text called deaths. Anything in single quote is just the text as it is. So you can see now I have the location, a text called deaths, and then the value of the deaths. I can also see what the other features look like. I can preview other features. So you can see now I have the location, space, the value, the text death, and then the actual value of the deaths from here. We can do a nice formatting. I want to construct this kind of text. I want to say whatever location name, semicolon, deaths, and the actual value of the deaths. This is the final expression that we want to use. This expression is given in your course material here. So you can go and use this expression and put it here. I'm going to also share it in the chat. So you can just copy that and paste it there if you want to. I'll explain the reason for adding a semicolon here, but for now, we're just constructing a label which has got both the location name and the total death in a single label. And we'll see how that helps us. Let's format it better. First thing I want to do is I want to not have the labels so long. I want to make them shorter, break it down over multiple lines. To do this, I'm going to use in the labeling panel, I have this second tab called format. So go and find this second tab. It says plus AB less than C. This is like a formatting tab. Here we're going to make a few changes. At the end, we have this option, wrap on character. That means whenever you encounter this character, break the line. Since we want our labels to appear the name and in the new line, the death value. So I'm going to use semicolon here. And you can see as I enter semicolon as a wrapping character, my label gets broken down into multiple lines. The second line has the value in the death. Since we had constructed this line, which has got the semicolon. So we put a semicolon where we want to break the label into multiple lines. And here we specify where you want to do this. We also have very long lines. So we can also break it down and limit the size. In the next option, wrap lines, we say 20 characters. So you can see now my labels are much more readable. They are maximum 20 characters. Whenever it encounters this semicolon, it breaks it down. So now we have the name, location, one or more lines, and then the next line, which has got the death count. Let's make the labels nicer. I'm going to switch back to the ABC section. This is the first tab in your labeling panel. You can change the font, whatever font you want, your choice. Size, you can adjust the size. I'm going to make them slightly smaller. So I'm going to use 8 points. And looking at the final map that we are aiming to construct, we want these labels to have a black background and the text will be white. So to replicate this, we want the label color to be white. We'll add the background shortly. But right now we just change the font size to be 8, the color to be white. So the labels are now white. You can change the font to whatever you want. And then we're going to go to this tab with a shield, the highway shield, the blue and red color that allows us to add a background. So once we're done, you can switch to the background tab and add a background to it. So this is the 5th tab with the blue shield, draw background, and the background can make it black. You can also add a little bit of buffer so that there's more space between the edges. So we can increase the buffer size, maybe 2 pixels to 2 pixels. You can see it has got added a bit of buffer to it. Bunch of options. Again, feel free to explore all the options. QGIS has literally hundreds and thousands of configuration options for labels and styling. I'm just going to show you a few. Here we have the boxes, which are all complete rectangle. We can make the edges a little rounder. There's a radius here. I'm going to add 5, 5 as radius. You can see my boxes get this round edges. Just gives a little bit nice effect to this. So after that, after changing the text to white, we switch to the shield tab, which is your background tab. Click draw background, change the background to black, add a buffer 1 or 2 points buffer so it's a little larger, and then add a radius to it, 5 points radius. Finally, we switch to this tab and enable the callouts. Callouts are these lines connecting the label to the point where it's labeling it. And you can see now we have this label, which is connected to the center of the point. You can adjust where the line appears. Labeling is a very hard problem in cartography. You have to decide where to place the labels. If you have lots of features, you have to decide which labels are more important, what to display on the map. QGIS has a very powerful labeling engine, which decides where to place the labels automatically. So if I'm zoomed out, it says, I don't have much space. I will try to best orient the labels so they don't conflict with each other. As I zoom in, my labels will move and say, I'll put it in the right place, even though sometimes you may not have enough space for all the labels. So QGIS decide to hide certain labels if you want. There are many other options here to say, these labels are more important, this ones are less important, and so on. When you have just a few labels, it is useful to just orient them manually. So let's not decide, let QGIS decide. I will place the labels manually, arrange them in exactly the way I want. You also, if you have lots of labels and you say, my map looks almost perfect, except this one label that is at the wrong place, you can also move that aside. So you can use both automatic labeling in combination with manual labeling. Here, we want to create a map that looks like this. We just have 10 labels. We can arrange them outside of the map region so that doesn't conflict with any of the data. Plus, we can arrange them so that it appears nicely. So let's learn how to manually move the labels and put them in the correct place. Let's save the project first. If you've been working on the project so far, it's a good time to save your work. The next step is a bit fiddly. Sometimes you'll do something and you'll say, my map got completely screwed up. So you can go back to the saved version of the map if you need to. Let me show you the process first, then you can try this out. We're going to take this labels and arrange them manually. To do this, we need the labeling toolbar. So I'm going to go to View, Toolbars, and make sure my label toolbar is open. If you already have it enabled, that's great. But this is what the toolbar looks like. So this is my labeling toolbar. It's got a bunch of options. We have this option here with an arrow next to ABC, move a label. This allows us to move the label manually and change the position. Let me use this. Again, first, let me demonstrate, then you can try this out. I'm going to click this button. The way this works is first you select a label that you want to move, and then click the place you want to send it to. So first time I click it, it's going to give me a pop-up saying that I want to save this label positions along with the QGIS project. And I want to make sure that I save it with a unique ID that has all the label positions separately. So say, show me which field in your data has a unique ID. If your data is saved as a geo package, FID is a unique ID. It's an internal ID that your geo package creates. So FID is always a good choice. Or any other field which has got unique values. So this will be used to save the label positions along with your QGIS project. So we'll keep FID as the default choice. And now we can say, click on this arrow icon, click on the label we want to move, and then place it where we want to move it. So now you can see I have moved the label. It has moved and connected the label. When you're doing this, do it one by one. Sometimes when you place something very much away from the map, QGIS will say it's not visible and it's going to go away. So if I do something and you say my label disappeared, you can bring it back. But if I do something and many times, if I put it somewhere outside, you can see one of the labels disappeared. If it's conflicting, it will move around. So do it one by one. You can arrange them so that the lines are not conflicting with each other. If you lose any of the labels and say, I have lost a label, there is a button here, toggle display of unplaced labels. So if you lose a label, you have moved it outside of the map or you've done something to do it, you can toggle this and the label will appear and you can go and place that. Let's try this out. Let's try doing the manual placement of the labels. Enable the label toolbar, choose the move label icon. The first time you click on a feature, you'll be asked to choose a unique field, choose FID, and then select the label, show it where to go. It'll be useful if you're zoomed out and show the full map so that this will be the final layout that you want to create. If you zoom out further, it says, I don't have space to put the labels where you had, so it'll hide certain labels. But you should always do this at the level that you want your final map to appear, so that the placement of the label is correct. And as I mentioned before, this is a bit fiddly. First time you do it, you may make mistakes, but try this out. If you want to catch up to this point, you can load the Checkpoint 3 project from your data package. The Earthquake Checkpoint 3 project will have our labeling formatting applied, and you would have them placed correctly. Let's do an exercise to practice some of the expressions and the functions to change our labels slightly. Vigna, you can explain the exercise.
So you see that in the labels, we have numbers and these are just long numbers and we want to format it in a way so that it is easier to read. And here you see that you can format these numbers like this. You can put comma here and you will have to modify the expression for the labels and you will just use this function format number. Wherever you are using the number, which is total depth, use this function around that total depth column, and you will see that after applying that expression, your format of this number will change and you will see the updated output. So try this, update your expression for labels and use this function there, and you should see the change in your label.
What we want to do here is we have this location name. We want to apply the function on this column. So the format number, you search for the function here. It has got some options here. You can see the different arguments that this function takes. You can give it a number and it'll just change the number. How many places to format to, the language. The formatting is specific to the different language or the domain that you have. So you can specify the locale that you have your QGIS configured and whatever system you use. So for example, in US, they use 1000 separator. In other places, they'll have dot separator and so on. So you can configure this. The only thing that you need to give is the first option. So you just say format number of this value and your label will change and you'll see the formatted output there. This is what we've done so far. We have learned how to load data, visualize the data, add labels, and we had this map. We'll now learn how to take the map that we've created and create a layout from it. This is the final map that we want to create. We have created the basic visualization with the labels, but to publish this map, we need to add some other elements to it. We need to learn how to add a title, add a legend to it. Now, right now, the legend is not on the map. We need to add it on the map. We also want to credit the data sources, add some logos, etc. So how do we create a layout from the map and get it ready for publication? So that's our next section. We're going to start working on the section 1.4, where we'll create a print layout from this. If you have been saving your work, you can start from there, or you can start from the Checkpoint 3 project, which is everything that we've done so far. QGIS comes with a very powerful tool called print layout, which allows you to do different kinds of map compositions. You can have a single map, you can have multiple maps, you can have one map with an locator map and so on. All kinds of layouts can be created using this very powerful tool. To create a layout, you can go to Project, New Print Layout. So let's go to project, new print layout. It's going to ask you for the name of the layout. Each QGIS project can have multiple layouts. For example, you can have a map and you can say, I want a portrait layout. I also want a landscape layout. Or I want a layout where I zoom in on a particular region. I have another layout where I'm showing a different region. If you just want a single layout, you can just leave the name empty. It'll be named layout 1. So well, let's just leave it empty and click OK. It's going to open up a new window. We're going to maximize it. This, at the center of your screen, is a canvas where you have essentially a paper, and you have to compose your map on top of this by adding different elements to it. First, let's decide what size of map that we want to create. Once you have the print layout open, you can right click on the map and select page properties. This will open up a configuration for the page. You can choose the page size and orientation. Right now, our map fits nicely in a landscape layout. So let's just keep it A4 landscape. But if you wish to change it, you can change it later on. You can also change the background color if you wanted to. Once you have the layout, you can use the tools here to zoom in and out, or you can use your scroll wheel to change it. The way the layout tool works is you are able to add and configure different map elements. If I look at the add item, you can see the different elements that I'm able to add. I can add a map, a 3D map, pictures, legend, north arrow, and so on. You can add multiple maps to it, or the same map with the different views. Let's go and select this add map, and you need to hold your left mouse button and draw a rectangle. Let's draw a rectangle from the top left corner up to some place, leave some space at the bottom for our bottom panel, but you can just draw a rectangle that spans most of the page. And as you do this, the map that we have in the main QGIS window will get rendered here. Ideally, you would first set the extent of the map to the one you want from the main QGIS window, and you can then do this. But this map view is independent of the main view. You can change it the way you want. You can also resize the layout later if you wanted to. If I click on this map and we want to change anything about this, we need to have certain panels available here. The one that we want is the item properties. If you do not see it, you can go to view, panels, and item properties. That'll bring up this dialog where you can select any item from your layout and configure its properties. So this is our map, and we have some properties. One of the stuff that you may want to do is you may want to adjust the zoom level or move the map around slightly. There are some controls available at the top of this map layout. You can see there is a button with a paper and 4 arrows. It says interactively edit map extent. If I select this, I'm able to move the map around and adjust its extent in the place that I have chosen. You can also adjust the scale here and to make the map more zoomed in or zoom out. I'm just going to make it slightly more zoomed in. So again, increase the value if you want to be zoomed out, increase the value if you want to zoomed in. If you have larger scale, it'll be more zoomed out. So you can adjust the position of this map within this frame that you've chosen using this button and move it around. You can adjust the scale if you wanted to adjust the zoom level. Most of the time though, it's just easiest to first adjust the zoom level here and then use the map layout. If I adjusted something here, so for example, I adjusted something here and I say, okay, now I want this view in my print layout, I can first adjust QGIS and then click this button, set map extent to match the main canvas extent, and then this map will change. So instead of adjusting this independently, you can go to main QGIS, adjust it, and then use one of those buttons to get the map extent from here. For now, my map looks fine here, so I'm going to leave it the way it is. Let's add some more map elements to it. We're going to first go and add a title. Once you have a map, let's go to add items, and there's an option to add a label. The concept is similar. You select the item, draw a box where you want the item to appear with your holding your left mouse button, and the label will be added there. So I'm going to select this, and I want my label at the top, so I'm going to draw a box at the top where I want my label to appear. And you can see right now it just has some placeholder text. I can change my text to more informative. So I'm going to name this map title as 10 largest earthquakes. So I'm going to change my title to 10 largest earthquakes. Again, you will see there is an expression button. You can also take the title from some element from your main QGIS or some variable or some expression. But our title is static, so we can just leave it like this. We can adjust the font and the alignment. To adjust the font, under the Appearance tab, you can click on this button, Font. It's going to open up all the font changes. You have a bunch of options here, what style of font you want. It's going to change it. You can change the size, make it 24. And you can change the alignment. There's a center and middle alignment. We've done two things. We've added a map here and we've added a label here. So we had gone to add item, label, added title, 10 largest earthquakes, 2000 to 2020, and adjusted the fonts and alignment. There are hundreds of options here. If you want to configure and do something different, see what options are available. You have, again, you can rotate, add a rotation, add a frame. So you want to add a frame around that, you can do that. So again, this has got so many options. You can design the layout and customize it to your heart's content. One very important element we want to add here is the legend. We want to explain people who are reading this map, what do these different circle sizes mean? And what are the other things that we've added to the map? So let's add a legend. You can go to add item and add legend. We can draw a rectangle where we want legend to appear. This is a nice place. It's empty. There's not much going on here. So we can place our legend here. And as you finish drawing the rectangle, as you draw the rectangle, you'll see the legend that we have in the main QGIS window will get updated here. So everything that we see in the main QGIS window, the same legend appears here. This is okay, but it's not very pretty. We have the layer names, which doesn't look very good. And we don't want certain items in our legend. So we can customize the legend. First step, once you have the legend, is I want to turn off this auto update in the legend items. If I turn off auto update, that means it will not copy stuff I have in QGIS. I can add, remove stuff to it. I can change the layer names and so on. So first add your legend, turn off auto update. Now we have some layers and some layer control here. First, I have this base layer for the landmass. It's pretty obvious what is it. So I don't want a legend item representing that. So I can select that, any 10 million land layer, click the minus button and remove it. And it's gone. This controls will be only enabled once you turn off auto update. Otherwise, auto update means whatever I have in my QGIS layers panel, the same legend will be copied here. You can also rename the layers. You can see this false layer is named gem active false harmonize. Not a very good name to appear in our legend. So we can just select this, and next to this minus button, we have this button with a pencil. It says edit selected item properties. So I can select the gem active false harmonize layer, click this button to edit the name, and I can just name it false. You can see my now legend item updates it to say this is all the false. This is just to show that the legend here is fully customizable. You can update the layer names. You can remove certain items that you don't want on your map. Similarly, we can rename this layer, significant earthquakes 2020. I'm going to rename it to be all significant earthquakes. Take this layer, and once you right click this item, you can just set it to hidden. So I have this large earthquake, you can just say hidden. And you can see it just hides that. So I already have the nice legend title, total deaths with the circles. So I can just right click this large earthquake layer and set it to hidden. One more thing we can do with the legend is we can add a border around it. If you scroll down on the legend side, there is an option to add a frame. So you can just tick the frame box, and now you can see there's a nice frame around it. So if you scroll down, there is an option to turn on the frame. You have an option to add north arrow if you want. The kind of traditional GIS thinking is that every map must have a north arrow. A more modern cartographic thinking is all maps or most maps are north up. So if your map is north up, which is the standard, you do not really need a north arrow. If you're creating a non-standard map where maybe the north is not exactly up, maybe it's off by 30 degrees, or you're creating a south up map, that's where you need to put a north arrow saying that this is where north is. So if you just have a regular map, the more modern thinking is you don't really need a north arrow. So you can skip that. If you wish to add a north arrow in your map, you can do that. Scale bar, again, a scale bar at this global map, you can add it. In our case, our map is more of an infographic. People are not going to use this to measure distances. So I don't think we need a scale bar. But if you wanted a scale bar, you can go and add that. We have an assignment where you can explore how to add different elements like a north arrow and a scale bar to a map. So you can practice that. In this map, we're not going to go and add those two elements. What I want to show, however, is how to add certain images and logos to your map. So let's go and add our next item, which is a picture. So go to add item and add picture. I'm going to draw a rectangle at the bottom right corner where I want to add some logos. Once you create this, you have an option to add some logo. There are some built-in icons that come in if you want to add those. One of the stuff that I like to do is if I create a map using QGIS, I want to tell people that I've used QGIS. If you also want to share that you have used QGIS, QGIS comes with a bunch of logos here that you can use. So if I see, once I draw the rectangle for add images, you can see there are a bunch of logos. This one says made with QGIS. So if you want to add this made with QGIS badge on your map, you can go and add that. So we go to add item, add picture. Under the SVG browser, there's a folder for logos. You can add, there are a bunch of QGIS logos here. You can add that here. And you can also change the alignment. So the logo appears nicely here. You can also add your own custom images. So let's go to add another picture. I'm going to add one more rectangle here. Here, I want to add a logo of my company. Maybe you want to add your university logo, your organization logo here. So you can click raster image here at the top and then browse to a file on your computer. So I'm going to browse in your data package. I have a logo.png, which is the logo of my company. So I want to add it here. If you have your own organization logo, feel free to add it here. If you don't have any handy logo, you can feel free to add this logo as well. It's almost done. We can add some information about the map itself and some data sources. One good practice is always to credit your data sources, where you got the data from. Many of the data sets also come with a requirement that when you use the data, you have to credit it. So if you create a map using some data set, the license may say you have to credit the data where you got it from. So we can add a bunch of those elements as well. I'm not going to spend too much time. I'm just going to show you how to add some labels. So let's say I want to add a label here. We can just go and say add a label here, where we can say, I would say, Introduction to QGIS course. We can add it here. We can also add another label. And we can add our data sources here. And you can go and credit the data sources that we had. So we use Natural Earth, we use GEMS, Faults, database, and then we use the NCEI earthquake. Again, this is just to show you that you can add something like this. The actual citation is given in your final map. You can follow that. Once you have this, it'd be nice to just add a nice footer section where all of this stuff is there. You can also add different shapes to it. So if you want to have a nice container items where you can place all these items, you can go to add item, add shape, and add rectangle. So I can add a rectangle and draw it around the different elements. And you can just make it a transparent fill with some solid stroke style. So this is a rectangle that I've added. I can also copy paste those. So I can copy it and put it around different elements here. This is a way to create some nice frame and border around different elements. Some of them have an option to create a frame by itself, but it might be just easier to have a unified frame. Once you create a style that you like, you can just add those as shapes. And of course, you can snap and create those easily here. You can spend as much time as you like configuring this, but this looks like a good basic layout that we have created. And once you're happy with this, you can now go and export that. Once your layout is done, you can also save it. So you can say, I'm going to save this. Once I save it, this layout is now saved within my project. That means if I close this, and I want to go back to the layout, I can say, go to my project menu, layouts, and now I have a layout that I've saved previously. So I can open the layout again, and it'll be created exactly the way I've created. So you can have your layout saved within a project. Whoever gets a project also gets a map along with the layout that you've created. I want to show you the final layout for this section. I'm going to load the last checkpoint project, the earthquake checkpoints 4 project. This comes with the layout that we have created for the final map. So I'm going to open project, layouts, and layout 1. And this has the layout that we have configured. Again, we learned how to add individual items and configure it. This has just got the data citations and frames done in a little nicer way. So this is the print layout we have created, and I said, this is great, I want to share it with somebody. You have 3 options for sharing. If you go to layout, you have an option to export this as an image. So this will export it as a PNG image or a JPEG image. This is great if you want to put it in a report, a paper, or in a presentation, or maybe post about it on social media. The second option is SVG. SVG export is great if you want to take the map you created and take it into a graphic software like Adobe Illustrator or Inkscape and finish off the map. Many times, most cartographers use QGIS as the starting point. So you'll use a GIS environment as a starting point to get all our layers, get all the labels, and then take the output of this into an Illustrator software like Adobe Illustrator or Inkscape, and then do the final map processing there. So if you want to do that, you can do this. Many QGIS users also use the open source program called Inkscape to design their maps. You can use that. If you're working with a graphics designer and say, I've created this map, say, okay, send me a SVG file and I'll finish it up. This is how you can export the SVG. So you can export it as SVG, and then they'll have all the actual shapes as vectors that can be edited or styled differently in a different software. The third option is a PDF. PDF is a great option where it's much more portable. You can share the file. They will have the map that is created. PDF also preserves the data as vectors. So many graphics designers will also use PDF to extract the data they need for their work. Let's first try exporting this as an image. So I select export as an image. I select the name. I'm just going to keep it as layout 1 and click save. We have some options, what resolution you want to export with, etc. And I'm going to click save. So it now will take this and render this out to a PNG file. Let's take a look at the exported results. We have this layout.1.png, and you have this image that we've created. And now I can send this image file and show people the map I've created. Another option that you may want to try out is export as PDF. If I'm saving it as a PDF, I have some options. The one option I want to share with you is this option called Create Geospatial PDF. A GeoPDF is an extension of the commonly used PDF format where it preserves all the geospatial information. And this is actually a vector format. That means if you save it, the PDF file will have the coordinates and the data layers saved as vectors. You can also save it and drag and drop it into QGIS, and it'll just load all the data layers. So if somebody says, I cannot share my data, I want to create a PDF, at least encourage them to create a geospatial PDF, which will work in any PDF software. People can view it. But if you have a software that understands GeoPDF like QGIS, you can actually drag and drop your PDF file inside of QGIS, and it'll have all the data layers by itself. Let's explore how to export our final layout as PDF. That's our exercise. Vigna, you can explain the next exercise.
So for your layout, you can export your map in the PDF format. And while doing this, you will see that you have this default checkbox checked, which says simplify geometry to reduce the output file size. This is useful to reduce the file size, but it sometimes create unexpected effects in your final output. So just export your output like the map in the PDF format and uncheck this before exporting it to see the clear map. And try this exercise.
And try checking the box, create geospatial PDF as well. Most modern versions of QGIS comes with the GeoPDF support. So you'll also see that once you create the PDF, it's interoperable. Any software like Adobe Acrobat will be able to see it, but you can actually go back and use that PDF file to have access to the underlying data layers as well. So this is something that I always encourage people who say, we want to share data in a portable format. Geospatial PDF is a good format. PDF is simply just an image. This will get people access to the raw data layers as well. We're done with this section. We're going to move on to the next part of our course on data processing and data visualization. As we start using QGIS for data analysis, we want to learn about this very important concept in GIS called joins. Many times your data will come with multiple layers. You want to join them and extract some information from two different layers. There are multiple ways to do this in a GIS. Let's learn some of the basic techniques for analyzing different vectors data and joining them to extract some information. You're going to learn about 3 different ways. When you have data in 2 different layers and you want to merge them, you can do it 3 ways. One is called a table join, where you have one vector layer, one spatial data, and some tabular data, and you want to join them to create some data set for mapping. That's called a table join. Spatial joins are data set where you have 2 vector layers and you want to join them based on their spatial relationship and create a new data set. That's called a spatial join. Third one is when you have a raster data. So you have maybe your population data and elevation data, and you have some polygons or points, and you want to extract the information from the raster for those vector data, and that's called raster sampling. Let's learn in detail what this means, and we'll also learn how to do all of this in QGIS. A table join will join one vector layer with a table. The simplest kind of join where you say, I have my vector layer, which is your shapes plus some table. I want to join it with another table based on some common attribute value. And you find the matching row from the table and join it with the polygons. Let's see an example. Here we have a shapefile of all the countries with one attribute called name. So we have shapes of different countries. We don't have any data about countries. The data comes in as a separate file. So you have an Excel file where you have a country column with the country name and another column, GDP per capita. And you want to create a map of GDP per capita. It's a very common operation where you say, I have some data, can we create a map out of this? How do we map this? The data that we have in Excel doesn't have any spatial information, but we can link it to a spatial information based on a common column. So here, for example, we have a vector layer. You can download a shapefile where you have country polygons, and for each polygon, you have information like this, where you say, I have the name of the country, and that's it. That's all my vector layer has. I have another table, an Excel file or a CSV file, where I have a country column along with some data. I want to map this data onto this map. So how do I get this data onto my shapefile? Well, you can see that they have a common attribute. Both of them have a column where they contain the same name. So you can say, I want to join this vector layer with this table based on this field name. And that means wherever there's a matching value from this table, it'll get added here. So once you do the table join, you'll get a new layer where you have your shapes with the original column plus the new column from your tabular data. And now you have a data that you can now use for mapping. This is very commonly used in mapping demographic data. If you want to map census data, you will get some shapefiles of the shapes of the census blocks, and then you will get a separate file which has got information about those census blocks as tabular data. And you have to do a table join, and then you can create a map of this. In QGIS, you can perform table join using this tool called join attributes by field value. We'll be doing this as part of our next exercise, where we'll create a population density map of New York City based on some data, which is polygons, and other data, which is CSV files. We'll do a table join and using this tool and create a map. The next kind of join that we want to learn about is called spatial join. This is a join where you have data in 2 different vector layers and you want to merge them together. Here's an example. You have a point layer of cities and you have a polygon layer of states. So you have one layer with points as cities and just have the name of the city. You have another layer, you have states, name of the states. You want to now join them so that you say, for each city, what is the corresponding state? I want to get those attributes. I don't have that in my point layer. I want to get them from the polygon layer that the point is intersecting with. Tool that you can use is join attributes by location. So you take your points layer, you have your polygon layer, and you just do a spatial join. You don't need any common attribute. You just say, I have my point layer here. I don't know the state that this belongs to, but I have a polygon file with the state names. So I can join this layer with this one, transfer the attribute of the state name onto this table. And once I do this, you'll get a new field, new table where you have the cities with the corresponding state. This is very useful where you have some data and you want to get, let's say, some zoning information or some other admin boundary information. You can take those layers and do a spatial join to transfer those attributes from an intersecting polygon back to another layer. You can do a spatial join in a different way as well. Let's say we have a layer of earthquakes and we have another layer of populated places. Earthquake happened, you want to know what's the nearest population center. Those points do not intersect with the other points. There's no common intersection, but you can use the tool called join attributes by nearest, which will say, I have a point, give me the nearest point from another layer. So now I just have that long of earthquakes. I have a point layer with the name of the city. I'll get a new layer with the earthquakes along with the nearest city. So here's an example. I have earthquakes. I have all the cities in Japan. I want to know what was the nearest earthquake to each city. And once I do a spatial join between these two layers, I will get the nearest name of the city. So now you can see I have the earthquake and corresponding nearest city to it. Quite useful. You can use this for doing all kind of mapping different disasters. You want to know the different hurricane falls and what was the site and so on. Spatial join, you can also do reverse one where you can say, I have a polygon. I want to summarize the stuff that is inside of that. Here's an example. You have the polygon layer of districts or counties. You have line layer of roads. You want to know what's the total length of roads in each county or each district. This is kind of a reverse spatial join. I want to take each polygon, find all the roads that belong inside and create the sum of lengths within that. So I want to create some statistics on all the intersecting features. This is also a spatial join. You can do it using join attributes by location, summary tool in QGIS. Here's an example. I have some districts. I have all the roads. Once you do a spatial join, you will say, I have the districts along with the summary of all the roads with that file within this. So there are different kinds of spatial joins that you can do in QGIS. Join attributes by location. If there's a spatial relationship, you can do this. Intersecting features, you can transfer attributes. Join attributes by nearest will find the nearest feature and transfer the attributes. Where you have multiple features inside a polygon, you can use the join attributes by location summary to summarize and compute the statistics on those features. The next stuff I want to cover is raster data. How do we extract data from raster using a vector layer? Let's say I have a polygon layer of river basins. I have a raster layer of rainfall. So we have each pixel saying that in this region, in this pixel, this was the rainfall. So I have a raster layer of precipitation. I have a polygon layer of river basins. I want to compute the average rainfall in each basin. This operation in GIS is known as zonal statistics. You have zones, which are polygons. You have raster, and you want to compute the statistics of all the pixels that fall within each zone. So in QGIS, there's a tool called zonal statistics where you have a polygon layer and a raster layer. You want to join them. This is the tool that you want to use. So here, this is what the raster precipitation data looks like. Each pixel is the amount of precipitation that happened in that particular year or time period. And then you have a polygon. And now you can say, I have this polygons. I want to know within this polygon, what was the average rainfall? I have so many pixels within that. I need to go and find the average value of those pixels. I can use the zonal statistics. And once I run the tool, for each polygon, I'll get a new attribute, which is the statistics from that rainfall. Next kind of raster sampling you want to do, if you have points and some raster. Let's say I have a raster of temperature. Each pixel is the temperature of that particular region. I have point layer of cities. I want to extract the value of the raster at each point. There's a tool in QGIS called sample raster values, which will extract the corresponding pixel from the raster layer. Another example is you have line layer of streets, you have raster layer of elevation. You have line layers of roads, a raster layer of BEM of elevation. I want to know the gradient of each street. A very common analysis when you want to understand, say, the bikeability of each street, or I want to understand what's the change in elevation if I travel on this road. So for this, there is a tool called set Z value from raster. So you take your line string and you extract the corresponding elevation values from the raster data. So these are the three different tools in QGIS that allow you to sample data from rasters, Zonal stacks where you have polygon and raster, sample raster values where you have point and a raster. Drape is when you have a line or a point and a corresponding raster. This is an overview of all the different techniques. Let's understand how to run these tools and work and solve a real problem using QGIS. So we're going to work on the next section where we perform a table join and create a population density map. You can open QGIS, start a new project. So we start QGIS, click on the new project button. The task that we want to do is we want to create a map of population density for New York City. This is the kind of map that we are looking to create. We want to create a map where we want to color each polygon based on the density of that polygon. So when we create a map, we say, okay, this is New York City. There are regions which are very dense, a lot of people live there. There are other regions which have low density. So how can we create a map like this where we can color each polygon based on the population density of that? This is a two-part exercise where first we'll get the data, source data, and then we'll process it, and then we'll visualize it. For this exercise, we're going to get some data. The data set we're getting is from the NYC Open Data Portal, data.city.of.new.york.us. It's a great data portal. They have lots of open data sets. I use it a lot in my courses and teaching because they have very different kinds of data sets that you can use. It's an open data, so you can go and download this. So the first data set we're going to get is the shapes, the polygons of something called NTAs, neighborhood tabulation areas. These are just polygons which have where they count different kind of demographics. They collect different kind of demographic information. So this, we can export this as a shapefile. And this is what we have done. So you have a shapefile of these polygons. It doesn't have any information. It just says this is the name of the polygon, this is the ID, and that's it. There's no demographic data that comes with this. So if you want to know what is the population in each of those polygons, we have to get the demographic data and link it with those polygons. The data is also available on the open data portal. The data is New York City population by neighborhood tabulation areas. And this one is just a CSV file. So this one is just data where it says, this is the area and this is the population. Just a simple CSV file. You can download this as a CSV or an Excel file. So now we have two data layers. We can't create a map from either of them. We have to first join it so that we have shapes along with the population of the people that live within that shape, and then we can create the map. So let's start working on section 2.1, where we'll learn first how to do a table join and merge these two data layers. We're going to open our data source manager. So click on this button. We want to load the vector data first. So go to the vector tab, and from the vector tab, click the browse button. In your introduction to QGIS data package, go and find this shapefile called nynta2010.shp. This is New York neighborhood tabulation areas for 2010.shp. The shapefile consists of at least 4 different files. You have to point to the main file, and QGIS will load the data from all of those. So let's load this nynta2010.shp. Click add. When you add a new data layer, QGIS will set your project CRS to match the CRS of the layer. So you saw that when you start, the default CRS QGIS opens in is 4326, that long. When we added this data, our project CRS was changed to this particular CRS. This is the CRS of this particular data layer. It's in projection called New York, Long Island, Kennedy 83. So this is a projection that is specific, which has got least distortion over this region, and your data set comes in that. So when you load it, QGIS will automatically set your project CRS to this and load this. You get the warning here that you use a ballpark transform. Most users do not need to worry about it unless you're doing very high precision geodesic calculations. This doesn't matter. The reason you get this warning is when your project is in 4326, you are reprojecting this data to 2263, you're setting this. There are multiple ways to transform this. These are not mathematical transforms. There are different ways to transform the coordinates from one coordinate system to another. There are different grids and different methods you can use. Each method will have its own accuracies. So QGIS says, I've picked one transformation for you. It may not be the most accurate one. You can go and change the transformation that you use. Most people, unless you're doing centimeter level calculations using this, you don't need to worry about this. So let's close this. Let's open the attribute table of this data layer. Right click, select open attribute table. You can see we have the attributes each polygon, if I select each polygon, you'll see where is the polygon. All we have is the name of the neighborhood and the code. That's it. We have the area, but we don't have the population. So if you want to create a map of population density, we can't just use this data there. We need some extra information to say, we have this neighborhood, what was the population there? And then only we can create the map. But note that we have this field called NTA code, which is a unique code assigned to each neighborhood. As long as we have another table where we have the same code along with the population, we can join those two layers. Let's close this attribute table. Let's get our next piece of data, which is the table for the population. Let's go to our data source manager. The data that we want to load is a CSV file. It's a text file. So we want to select the delimited text layer, click the browse button and select this file from the data package. It's called New York City population by neighborhood tabulation areas.csv. Open it. The file format would be CSV. And since this data is not a geographic data, we don't have lat long, we just have, it's a table. It's a table of the code of the neighborhood and the population. So we can just select the no geometry setting here. And you can see a preview of the data. And if you see a preview like this, you should be good. This is what the data looks like. And once it gives you a preview like this, you can click add. File format would be CSV, and you have to select the no geometry here. Click add, and we can close this. So now when we added this, you get a new layer, which is just a table. You can see there's a table. There's no polygons or points attached to it. Let's open the attribute table of this new layer. Right click and open the attribute table. Here we have the neighborhood tabulation areas. We have the name and the code. So the similar code was there in our polygon there, but we have this population column. So now we know the population of each of this neighborhood. And now we can say, I want to join this table with my polygon layer based on this common attribute called NTA code. If I sort the table by NTA code, you'll see that each NTA code has two entries here. We have population for year 2000 and we have population for year 2010. Now we are creating a map of population density for 2010. Even we have the polygons for 2010. So we need to only keep rows where the data is for 2010. We want to remove all the data for 2000 and then we can do a join. To do this, we can use something called a filter. In QGIS, you can apply filters on any vector data and select a subset of data. So let's apply a filter where we'll filter out data which is not from year 2010. You can right click and choose this option called filter. We're applying filter on the table where we have two entries for each neighborhood, population for 2000 and population for 2010. We only want the population for 2010. So select the filter. We'll bring up this query builder dialog. You can select the field that you want to apply filter on. So we can say year. I can double click this field. It gets entered in the query. You can say year, then click the equal to, and then we need to have the value. If you don't know what the values are contained, you can click this all button. You can say this field has only two values, 2000 and 2010. So I can say I want to select only 2010. So we can build our expression which says year equals 2010. This is select all rows where this expression is true. So all the rows where year equals 2010 will be selected. Rest, everything will be removed. And this is like an Excel filter where the data doesn't go away, it just hides it. It's not used for any analysis. You'll only see the data that matches this filter. So if you see the data and you say, I want to get back to all the data, you can click on that filter, remove the expression, and you'll get all the data. So this is a way to kind of restrict the analysis to a certain subset of data temporarily. Let's open the attribute table and see it. Here, now we see the attribute table. If I sort it by NTA code, you'll see only one entry for each of those values. Here at the top, it says 195 features, filtered 195. This filter is the filter view of your attribute table. It's not your layer view. So you can apply another filter on this and say, temporarily, I want to see the attribute table with some filters. So your data has been filtered. As if you see 195 features, you're good to go. You have one entry for 2010 for each of your NTA code, and now we can do the join. You can also verify the feature count. There's a handy tool where you can right click on each layer and select this option, show feature count. So if I show feature count here, it says 195. I right click here and say show feature count, it's 195. So now I have one-to-one match for each polygon. I have one corresponding entry for the population. And now I can join these two layers based on the common NTA code attribute. When we want to do any sort of joins or any analysis, all the tools are available in a place called the processing toolbox. Let's open the toolbox, go to your processing menu and select toolbox. The processing toolbox will open as a panel on the right hand side. This contains all the tools that QGIS has to offer. This toolbox contains hundreds of tools that allow you to do all sort of analysis. So when you want to have some data and you want to do some data processing, this is what you open and you can search for the tool that you want. Here you can search for, if you know the name of the tool, you can search for that. For example, we know that the table join can be done using this tool called join attributes by field value. So we can go and find the tool. If you do not know the name of the tool, you can also search for the name of the algorithm that you want to use. So let's say I want to do a table join. I can just search for table join and you'll go and find all the tools that allow you to do table join. So even if you don't know the name of the tool, you can search for the process that you want to use and it'll pull up the tool for that. We're going to use this tool called join attributes by field value. So go and find this tool and double click on it to open it. Once you open, you'll get a dialog box like this. First, we open the processing toolbox. So from processing menu, open the toolbox. You'll open this toolbox on the right, search for table join, and you'll get this particular tool, join attributes by field value. Double click on it to open this here. Let me show you how to configure it. Then you can go and configure it yourself. Input layer. The input layer in a table join is always the vector layer. The polygons that we want to join the attributes from table. So the input layer is our polygon layer, and it says what's the field containing the field where you will have common values. So we'll use the NTA code as our field value. The input layer 2, which is the join layer, which layer you want to join, we select the table that we want to join it with this. The table field 2, what's the field name in the table layer which has got the same value as the first field, and that also will select the NTA code. And this says wherever there is a matching NTA code between these two layers, join that particular value. Next, it says our layer 2, our table has so many fields. Do you want to copy all the fields to the main layer? We can click this 3 dots and say, I'm not interested in all of that. I'm just interested in the population, right? We don't care about anything else. So it says, don't copy all the layers, we just copy the value of the population. There are options. What if there's no match? So what do? What if there are more than one match? So there are different options for doing this. Right now we have 195 inputs, 195 join features. So we just say 1-to-1 join. So we can select this. And at the end, we need to configure and save the output. By default, when you run the tool, it'll create a temporary layer. We want to save the layer to a file so we can later use this. So at the end, where you see this option, joined layer, the default, it says create a temporary layer. We don't want that. Click this button here and say save to file. So we'll create a new layer. We also want to save this to disk so that we have those files and we can use them directly. Save to file. The format will keep it as GeoPackage. In your data package, you can go and save this as NYNTA with population. So name your layer as NYNTA with population. Give descriptive names. So when you find some layer, you know what it contains. So we're joining the population with NYNTA. So we name our output layer as NYNTA with population. And click save. Make sure the output format is GeoPackage. Once it's configured, your dialog box should look like this. And now you're ready to run. So once you configure it like this, go and click run. Click run, you'll see some progress bar and you'll see some output. It says 195 features from the input layers were successfully matched. So our table join was successful. For each polygon, it could find the matching attribute value and it joined the population value to our polygons. So we have polygons, we have the population. We want to create a map. We'll shortly learn that you cannot create a map by coloring polygons based on their population. you have to do some data scaling. You have to normalize your data based on either the area or other variable. The best way to normalize this population data is just by using the size of the polygon. So instead of mapping the population, we want to create a map of population density, which is just the population divided by the area. So if you say this is the number of people, this is the area, we can compute density in number of people per square mile, square feet, and so on. So let's add one more field here. We'll compute a new field, which is the population density, by dividing the population by area here. To create a new field, we search for a tool in the toolbox called field calculator. Go and search for the tool in the toolbox. This is a tool that allows you to take a layer and add a column to it. Once you find it in the toolbox, double click on it. Make sure you use the field calculator from the toolbox. You have another field calculator that's available in the toolbar. That's a different field calculator. Do not use this. From today onwards, you should all be using this field calculator, which is the modern version. It's got more features and it's just a modern way of field calculator. Double click on it to open it. I'm going to explain how to configure this, and then you can try this out. So input layer will be the new layer that we created, NYNT with population. The new column that we want to add is the density. The field type is decimal, that's fine. You want to write an expression. Here to construct an expression, we have our expression engine, the same one we had used with our labeling before. We can pick the fields that we want from here. So we can have the field column and say, I have the population and I want to divide it. So there's a forward slash is a division operator divided by shape area. So this is your mathematical operation which says take the population value divided by the area. Now the population is number of people. The area, if you read the documentation for the layer, it says the area is in square feet. So here the answer we get is number of people per square feet. Now this doesn't make sense. You do not want to know the density in population per square feet. You want to know population per square mile. That's a more common unit for density. So we need to convert the resulting value to population per square mile. 1 mile is 5280 feet. So a square mile is 5280 times 5280. So if you multiply this number by 5280 times 5280, we'll convert this value, which is population per square feet, to population per square mile. So I'm going to add an expression here which says 5280 times 5280 times this whole number. This is the expression that is given in your course material. I'm going to copy paste it. This is the expression that is available in your step number 24 in your course material. So this expression now will compute the population density. You can see the answer here. This is in this particular neighborhood, we have 62,859 people per square mile. That's a population density. And that makes much more sense. Once we configure it, we want to save it. So I'm going to save this to a file and we will name the file NYNTA population density. Output file geopackage. On Mac, sometimes the dialog disappears. You can use command tilde to bring it back. Go and configure your tool like this. Try this out. We have the field calculator tool from the processing toolbox. Input is NYNT with population. Density is the name of the field. This is the expression. Population divided by shape area in conversion to miles. And then the output field name, output layer name has to be NYNT population density. Once you configured it, click run. Let me run this. The processing finished. Let me open this final output. I'm going to open the attribute table. My final attribute table would have my polygons with the NTA code along with the population. Oops, sorry, this is the new layer. So my new layer is the NYNT population density. Let me open the attribute table. We have the NTA code, the population, and the computed value that we did, which is the population density in people per square mile. We have a bunch of layers. This is the only layer we need, right? We don't need other source layers. So it'll be nice to remove them from our project. You can right click any layer to remove it, or you can select a layer, hold shift key and select a bunch of layers. So right now we can select all these 3 layers, right click and remove them. So only keep the NYNTA population density layer, remove all other layers. And once you have your final layer, go ahead and save your project. We've done our work, we loaded our joint layer. did some computation, and we are ready to visualize this layer. But before that, let's save the project. If you want to catch up to this point, you can now load the checkpoint project. I'm going to show you the checkpoint project from the solutions directory. And NYC population density checkpoint 1. Your output would be the same as what is contained in the checkpoint project. This one has the density layer is the same as what we computed. So if you want to catch up to this point, you can load the checkpoint 1 project, and we're ready to do our challenge for this section.
So for the challenge here, if you will look at the attribute table, you have the density and you see these are some decimal numbers. The challenge is to convert it to the nearest integer. So you can use the field calculator. We just saw, you can just go to your processing toolbar and search for field calculator. So use field calculator, and there is a round function. Use that round function to round the value of density and create a new column called density round, and you can save the rounded numbers in that particular column. So try this, use field calculator and use the option round to round off the values of density.
We're doing the challenge 2.1.1. We have some hints here. That idea is again to explore some functions available to you in the expression engine. So try this out and try to create a new value with the rounded value. Let's move on. We are now ready to visualize the population density in our data layer. But before that, we want to cover a very important concept when you are creating maps based on some values. And especially when you're creating choropleth maps, you need to be aware of the concept of data normalization. Let's open the presentation. When you're creating a map and you're showing some data on the map and you want to communicate the magnitude of those values based on color, you need to be aware that there are certain, unless you normalize your data, you can miscommunicate the information that is present in your data. There are different kinds of maps. You can create a reference maps. So reference maps are like topographic maps or like Google Maps. You can use them as present the world, and all the information is there. People use it to navigate and to find places. Thematic map, it presents information about a particular theme. The earthquake map that we created, it doesn't contain every information on the region. It just says we'll focus on earthquake and we'll add information relevant to that. The most common type of thematic map that people create are something called choropleth map. It's not choropleth map, it's choropleth. This word comes from the Greek term choros, which is region, and plethos, which is magnitude, where you assign colors to different regions based on the intensity or magnitude of the values there. And you can color this, and you have this colored map, which shows how the values are distributed across the region. This kind of maps are ideal to display things like density or percentages or rates. They are not suitable for absolute values. So whenever you are presented with a polygon layer and you want to color those polygons, you have to make sure that the values that you are using are not absolute values, they are normalized values. Now, what do we mean by that? What do you mean by that? Let's take a look. If you do not normalize it, your map will end up emphasizing features which are larger in size. Typically, larger regions will have more people, more occurrence of all the different kind of phenomena they're trying to map. So unless you normalize it by the size of the population, you'll always say my big regions will always be in darker color, small regions will be in lighter color. And that doesn't convey the right information. Let's see an example to learn what happens when you don't normalize the data. Let's say we want to create a map with some demographic data. We want to create a map showing the literacy in a region. Let's say we have data and we want to understand literacy, and we maybe are tasked with understanding and improving the literacy in the region. This is what our data is. We have 4 polygons for different values. This is, there are 15 people literate in this region. There are 10 literate people in this region, 10 literate people in this region, and 5 literate people in this region. If you want to create a map, a more common temptation would be to just say, let's assign some colors. 0 to 5 will be red, 5 to 10 will be yellow, greater than 10 will be green. And you can create a map. And you can say, here's a map of literacy in this region. What do you see? When you see this map, what do you understand? You say, okay, this region must be really good. They're doing well on literacy. This region is doing pretty bad. It could be that this region is doing well, this is bad, but typically larger regions will have more people. Maybe there are just more people here and there are less people here. It is like comparing Finland to US. There's so many less people in Finland, you can't compare it to US unless you take into account the population. So let's look at this map. Remember what it looks like. Let's create a correct visualization out of this. We have a number of literate people. Let's get the population. So say in each of this region, these are the number of people who live there. So in this large polygon, there are 45 people who live there. In the small region, there are 5 people who live there. So now we compute the literacy rate, number of literate people divided by the total people. We get values like this, where in this region, there are only 5 people, everybody is literate. So we have 100% literacy rate. In this region, there are 15 people who are literate, but there are 45 people who live there. So there is a 33% literacy rate. And now if we color these polygons by literacy rate, we get the correct picture. Now we know which region is doing well, which is doing bad. You get a very different picture if you don't normalize the data. And when you want to create a map, make sure you always normalize the data. It's not a very intuitive thing that happens. Many people, many beginners, even very experienced GIS folks make this mistake, where you're trying to display some information using colors. You have to normalize the data. There are many cartographers who critique maps openly. There are some examples of cartographers saying you should never display absolute values. During COVID, people used to publish maps like this. Number of COVID cases in this region. Well, of course, if you have a region which has got 100,000 people, you'll have more COVID cases versus a region with 1,000 people. So you want to say the COVID positivity rate. So number of COVID cases divided by the total population, that gives you the true picture of how people are managing COVID. Just displaying absolute values on the map, it gives the wrong information. Other thing, number of data centers in each country. And you say, where are the more, if you see the map, you say, oh, in US, India, and Australia, maybe there are more data centers. Well, obviously, there are more people, you need more data centers to connect them. But if you normalize by the area of the country or number of people, you will see that a lot of people places in Europe are doing much better. They have much more data center per capita or per internet user. And that will give you the correct picture. So again, when you're creating maps like this and colorizing them, make sure you normalize the data. How do you normalize the data? Population or area is the most common attribute to normalize. So you never create a map of population. You always map population density. So divide by the area of the polygon, that will normalize it. You can calculate rate, so divide by population, and you say literate people divided by total population, literacy rate. COVID cases divided by total population, COVID positivity case. If you want a map of unemployment, again, don't just create unemployment map, just say unemployment people divided by total working age population. Find the parameter where you can, once you normalize, you can compare apples to apples. If you want to have urban map of urban population divided by total population, calculate the percentage based on that. If you want to map, let's say COVID Delta variant divided by all total new COVID cases and say, this is where there's more Delta variant, not just absolute value, divided by some variable where it helps you normalize the data. We want to now create a choropleth map for mapping the population density. We have the data for New York City that we have computed in the previous section. Let's be able to map and visualize which are the regions with high population density, which are the regions with low population density. Let's switch to QGIS. Let's switch back to QGIS. We're starting with our checkpoint 1 project. We have the NYNTA population density layer. We have computed the density. We have this density, and we want to use this density and colorize polygons where the low density regions will be in a lighter shade. The high density will be in darker shade. And we can now visually see which are the regions in New York which are highly populated. Let's open the layer styling panel. So go ahead and select this paintbrush from the layers panel to open the layer styling panel. Currently, we have applied a single symbol to all the features. That means all the features have the same polygon and same color. We want to change the symbology to be graduated. This symbology is useful where you want to use an attribute and say, I have a continuous values from low to high. I want to assign some color based on those values. So let's select the graduated symbology. When you do this, the map will disappear. Don't worry, we'll get it back. Once you configure it, your map will come back. So we have a single symbol. Go back to graduated. In the value column, it says, what value do you want to use to map? And this is a variable that we want to use to map. Select density. This is the range of values that we want to visualize. Next, we have a color ramp. We have values, default is white to red. If you click the drop down, you have choice to select many different color ramps. You can go to all color ramps and you can see different ones. For this one, let's use this color ramp, yellow, orange, brown. It says YLORBR. From the main window, you click the drop down next to the color ramp. go to all color ramps and select yellow, orange, brown. That means our low values will be yellow, high values will be brown. Number of classes, how many buckets of values you want to have from low to high. Change it to 6. Well, I'll explain why 6, but for now, let's just do 6. Change the number of classes to 6, and then click classify to see the results of your configuration. So once you change the values to 6 and click classify, you should see a map like this. You can use any color ramp you want. Just for this exercise, you're using this one. Feel free to use a different color ramp that explains your data or looks better to you. So we now have a visualization. You can now see which regions of New York are dense. This is Manhattan, very dense region. This is Central Park. Nobody lives in Central Park, so it's a less population density. We have Staten Island, again, less population density. So now we have this visualization we have created where each polygon is colored based on the value it has. By default, QGIS chose some range of values for each bucket. The default way it chooses this bucket is we want to divide the data into 6 buckets. It says I'll put equal number of features in each count. Let's say there are 100 polygons and we have, or let's say we have 100 polygons and we want to divide into 5 classes. Each bucket will get 20 features, and it tries to divide the data so that each of these regions have approximately equal number of features, and it chooses those range of values. If I right click and say show feature count, you'll see that all the buckets have now about 32 features. And this is what QGIS chose, saying that I'll choose the bucket so that each bucket has approximately the same number of features. That's your quantile mode of classification. This is good, but I personally do not like automatically decided bucket ranges, because if you create a legend, you'll say, what is this brown color? And you say, oh, brown color is 53,369 to 70,588. It doesn't really mean anything to the reader. It helps if our bucket values are more interpretable. So if you're creating a map like this, you can have your ranges designed so that they are more easy to interpret. Let's change those values so that we don't want this automatically determined values. We'll just create our own. We'll create a classification where we say density 0 to 20,000, 20 to 40,000, 40 to 60,000, and so on. We'll change those buckets. Let's see how to do this. I'll show you, and then you can try this on your own. This values, each row is clickable. If I click on the value column here, if I double click on it, it opens up saying configure this. It says lower and upper, it says 0 to 20,000. That's a first bucket. So this color will be assigned to all polygons where the density is between 0 to 20,000 people per square mile. You can keep clicking and keep doing this in the 20,000 increment. So we do this 40 to 60,000, 60 to 80,000, and 80 to 100,000. And the last one is 100,000 to the highest value that we have. And now my ranges makes a lot of sense. If I see a color, I can say, okay, this must be between 60 to 80,000 people per square mile. Go and try this out. Go and change those values. You can double click on the values column and change the range of values so they are much more interpretable. You can do 0 to 20, 20 to 40, 40 to 60, 60 to 80, 80 to 100,000. Last one, will let it be like this. We'll fix that. These are the actual data ranges that are used to assign a color. This is the value that appears in your legend. Here, it's the same. In your legend, you can see, people, when you create a map, you'll see this legend. We can also change the item that appears in legend. So for here, it's okay. For the last one, this is not a really good value. What we want to do is you want to double click and say the legend, you can just say greater than 100,000. So this is what this bucket represents. Any value that is greater than 100,000 is assigned this dark brown color. So you can see my legend now changes where the label for this bucket has been changed to greater than 100,000. And this is all text. You can change it to whatever you want. If you want to catch up to this point, you can go to your solutions folder and load the project NYC population density checkpoint 2. This will help you catch up to this point where we have created the symbology and we have this population density map of the New York City. Let's do the exercise. Vigna, you can explain the next challenge.
So here we want to get, or we can say we want to create a new layer with features where we have population density greater than 100,000. So you see all these, dark areas are the counties with density greater than 100,000. So we want to extract those. We have a tool called extract by attribute. So you can just go to this toolbox, processing toolbox, search for extract by attribute. And here you will see that you can just choose the attribute and you can just give the value, use the greater than operator and extract the layer out of this. So just try to do this, search for the tool, configure all the parameters, and then you will see the extracted layer.
So we've done the visualization and it's great to see this on the map, but let's say we want to extract those features in a new layer. Maybe we want to style them differently, or we want to send to somebody and say, hey, here are the regions that are more than 100,000 population density. So I want to save those regions out as separate layer. How do we do this? And this is an analytical operation. So we need to use the processing toolbox, go and find the tool from the processing toolbox that will allow you to do a query and extract those features as a new layer. We've learned how to create maps and we've learned how to do some analysis. We've not explored the full capability of the print layout. So your assignment is to take the data that we've just created in the second part of the exercise, and we want to create a map with all the different map elements. So your assignment is to create a map that may look like this. Feel free to use your creativity and your styles to create a map in your own style. What we want to create is a print layout which shows the New York population density. We want to add stuff like a legend. So you can add a legend, a north arrow, a scale bar, attribution, logos, along with some information. And you can create a layout based on your liking. So here's just an example of what, one of the ways you can do the assignment. You can also create a totally different map. The idea is to explore the capabilities of print layout and see what is capable of. So you'll take the data from the previous section. So you can load a checkpoint project, or if you have done your work, you can have your population density map. Feel free to use a different color ramp, style it differently, use some layer effects and so on if you wish to, and create a print layout map with these different elements on it. Once you're happy with the map, you can export it and save this as a PNG file. You're going to learn georeferencing and digitizing. This is also going to show you how powerful maps are and how you can use them to detect changes, to identify and do some really interesting analysis. Let me give you a bit of background on why we need to do georeferencing. Georeferencing is a process of assigning coordinates to images and even vector data. So we have an image and we want to place it on Earth, on the surface of the Earth. So we can locate every pixel of the image. Typically, the way you do this is you have certain points where you know the coordinates of. So you have an image, let's say you took a photo from satellite, or you took aerial imagery and you want to locate it where it is on Earth. You have a few points which are called tie points, where you say, I know the coordinates of certain points. And by knowing the coordinates of a few points on that image, you can place it on the correct location. And that's a process called georeferencing. There are some automated processes, there are some semi-automated processes. There are also manual processes that we have available in QGIS, where you manually identify those tie points and say, I know that this is the same point in both of those maps, where one is an unreferenced map or an image, another is a reference map. And you can show a pair of few of those points, you can tie them around. To see how this can be useful, we'll take a problem where we'll take the map for city of Bangalore. So let me just set up the problem. This is the city of Bangalore in India. It's a fast growing metropolis. This city used to be called the City of Lakes, where there were literally hundreds of lakes around the city. And as the urbanizations happened over the years, most of the lakes have been lost. And many activists, many nonprofits, many people who are trying to stop the effects of urbanization and climate change are now trying to preserve those lakes. One of the things they want to understand is how the lakes, which lakes have been lost, what happened to all those lakes. If you see the current map, this is the OpenStreetMap, you see there are a few water bodies in the city, but many of the city areas were built on lake beds, but we don't know where those are. We have to go back in time. So one option we can do is we can find a historic map. Here's a page I found on Wikipedia, which had a lot of historic maps that people had scanned and uploaded. So there are old maps of Bangalore, and these are maps that were paper maps, and then people had later scanned. They are not GIS maps. But you have an image that looks like this that showed the city, how it existed maybe 100 years ago. And you can see this image shows there are so many different lakes that were there. So we can pick one of those maps. Let's say this is a map of 1924. Exactly 100 years ago. And this is a map that shows all the different water bodies that existed in the city. And we want to now overlay this map on the current map to identify which lakes have been lost. So that's the exercise that we're going to do. We're going to first figure out how to georeference this map. So it overlays exactly on the map, the current map, and then we're going to go digitize each of those water polygons, compare it with the current base map, and create a map of all the water bodies that have been lost. It really helps you understand the history of the place and identify what happened in the course of the 100 years. After the class, after you learn how to do this, I encourage you to find a map of your own city, an old map, and try to replicate the process. You'll understand how QGIS works. Also, you'll get to know how the place changed over multiple years. So let's go and get started. This is a plain JPEG image. There's no georeferencing information. The first step, I want to now overlay this on the current map of Bangalore. Let's get started with our section 3. We want to get the current map of Bangalore. We want to get the currently georeferenced map. The best map that exists, which is free and open, is the OpenStreetMap. So let's get the current OpenStreetMap map loaded into QGIS. We're going to switch to QGIS. I'm starting our exercise on georeferencing. First thing we want to get some base map. We're going to use a plugin called Quick Map Services. We've already installed this plugin when the course started. If you haven't done so, you can go and install it right now. We need to go to Plugins, Manage Install Plugins, and we need to search for a plugin called Quick Map Services. If you haven't installed it, I'm going to give some time for you to go and install this. Most of you should have it already installed. So we're going to use this plugin to load some base map. Single word, Quick Map Services. Once you install the plugin, the Quick Map Services plugin adds a menu item to your QGIS under the web menu. So you should all have a web menu. And when you go to Quick Map Services, you'll see different base maps that you can load to QGIS. The very first time you install it and use it, you will see a very short list. You may not see all the base maps that are available. So the very first time you use it, you'll need to go and configure and add some additional base map. So let's do that first. Let's go to Web, Quick Map Services, Settings. So click on this Settings button. This would be under Web, Quick Map Services, Settings. This will bring up the Quick Map Services settings, the multiple tabs. Let's switch to the last tab, which says More Services. The plugin does ship with many base maps, which you may want to load to QGIS, but there's a warning that says you need to be aware of the terms of service of different base map and abide by those. The plugin distributors are not liable for that. So if you agree with that, you can click this button called Get Contributed Back. The plugins ships with the base maps which are completely free and open, such as the ones based on OpenStreetMap. There are other base maps which are shipped by companies like Google, Microsoft, Esri. They may have different terms of services and restrictions on what you can do with those. So that's why there's warning that you need to read those terms of services and use them in accordance with those. Click this button, Get Contributed Back. And once you do this, you will have a lot more services in your OpenStreetMap Quick Map Services folder. Let's go to the web menu again. Quick Map Services, you should now have all the different base maps. The one that you can use with no restrictions on licenses and can do essentially everything that you want to do in a GIS environment is the OSM base maps. So this is the one that I always use when I'm working on a project. I need a map as my base map. I need to digitize on top of it. I need to use that as a reference. These are good base maps to start with. So let's go and get the OSM standard base map. OSM is the OpenStreetMap, and these are the web map tiles based on the OpenStreetMap data. This is the OpenStreetMap rendering of the base map data that they have. It's a fairly detailed, really nice base map. Later in the course, we'll learn how to extract the data as vector layers and do analysis with this. All of this data is also available for analysis. Right now, this base map is just image layer that is added as a reference, but these have real coordinates. That means you can now extract the coordinates and reference information from this and use them to georeference any map that we want to use it for. QGIS has a built-in geocoder. That means if I want to go to a place and I don't want to zoom and find the place, I can use the search bar at the bottom left. So go to the bottom left of your QGIS where it says type to locate. Here you can search for a variety of things. If you want to search for a place, the key for this is this greater than symbol. So if you type greater than and then space and then type a city name. So let's say I'm going to search for New York City. So if I say greater than space NYC, it's going to search for NYC. And once I search and click for it, I go and find that place. So this is a place search that is built into QGIS. You can try this out and search for your own city name. In the search bar, you need to go and search greater than space and then the city name. So let's say I want to go to Bangalore, I can search for Bangalore and it's going to pull up all the results. You can double click on it and I'll zoom into the city of Bangalore. Quite handy if you're working on a map service, if you're working on a project and you want to zoom between different places. You don't need to manually do it. If you want to catch up to this point, it should be the Georeferencing Checkpoint 1 project in your solutions folder. So in your solutions folder, if you load the Georeferencing Checkpoint 1, you should be at the same place. So this has the base map, and we are now centered around the city of Bangalore in India, where we are doing the georeferencing. Let's do a quick exercise and see how we can load different kind of base maps. Vikna, you can explain the exercise.
So you can try this one, or you can just try another base map, which is Dark Matter base map by CartoDB.
So this one is one of my favorite base maps to use. It's a dark theme map and it's also a minimal map. So if you want to have a base map which just shows minimal labels, and if you want a base map which is minimal and has a dark theme which serves as a nice reference for your data, you can use some of those maps. So CartoDB has a couple of good maps. You can also check out other base maps. Many people like to use the Google Maps as the base maps. It's a good reference map for locating things. Also, there are many base maps by Esri and other providers. So check out different base maps, load your favorite base map from the quick map services, zoom into your city and see how it looks. Let's start georeferencing our map now. We have loaded a base map. This base map is georeferenced. So that means we have the coordinates. As I zoom and pan around the map, you can see as I'm hovering, I can see the coordinates. The CRS of this base map is EPSG 3857. This is the web Mercator projection. Almost all the base maps come in this particular CRS since they are on the web, and all the web maps are in this particular projection. So the WZ84 pseudo Mercator EPSG 3857 is the CRS of those coordinates. So what we want to do is we want to overlay our unreferenced scanned map image on top of this. So we can compare them and say how the city was 100 years ago. In your data package, we have this PNG file, bangalore1924.png. I will just open and show you. So this is our PNG file, and we want to now overlay this on top of our base map. The way we do this, we'll say the image and the map, they have some common elements. Even though 100 years have passed, there are certain elements which remain the same. For example, you can see this lake. You can see the shape of the lake is quite easily identifiable. So I can say, oh, the corner of this lake, I know the coordinates of that because I can see it from the OpenStreetMap base map, and I'll assign that coordinate to this point in the image. And if I assign a few of those, then there are transformation algorithms that QGIS applies, and then makes sure this image is rotated, skewed, and fit on top of that. So we don't need to find coordinates of every pixel. We just need to find coordinates of a few pixels. Let's see how we can do this. This is our section 3.2 from a course material on using the georeferencer. We're going to use a tool called Georeferencer. Go and open the tool from the layer menu, layer Georeferencer. In the older versions of QGIS, this georeferencer only supported images. So you can only assign coordinate information to images. In the current version, it supports both vector and raster. That means if you have some AutoCAD files or unreferenced vector data and you want to assign projection to that, you can also use this. So you can georeference both vector and raster data using this georeferencer. The process remains the same. You're going to learn how to georeference our image using that. But if you have some unreferenced vector data. Typically, those come in as like DXF files or DWG files. You can open this and then use the same tool to assign coordinates to that. Let's open the georeferencer. This is the georeferencer window. We have a canvas here, and we have a table where we'll see the points. If you do not see the table, you can go to View, Panels, and GCP table. For some folks, sometimes it may be disabled. So make sure you see a table of coordinates at the bottom. If you do not see it, you can enable it from View, Panels, and GCP table. Okay, let's load our image. In the georeferencer menu, there's a toolbar here. You have the first button here, which says Open Raster. So if you want to georeference an image, you would do this. There's also Open Vector. So if you have a vector data which is not georeferenced, or it's completely wrong georeference, you want to transform it, you can also use this tool. Let's click the first button, which is the Open Raster. From your data package, go and show this file, Bangalore1924.png, and open this up. You should see the image loaded here. And now we want to have a few points from this image where we need to assign coordinates. Here we need to find common features between those two areas. If you do not live here or not familiar with the city, I don't expect any of you to be able to do this very soon. But if you use it with your own city, you can do this. I'm going to show you a few points which are noticeable so you can practice and try. We also have the pre-saved type points that you can use to complete this exercise. But let's go through the process. Good type point is, you can see there's a lake. This is a peculiar shape of the lake, which still exists today. So this is the shape of the lake. So what we want to do is we can say, I know the shape of the lake, and even I can identify a corner and say this corner is the same as this corner on the map. So the coordinates of this corner can be assigned to this pixel on the image. So first step you're going to do is, there's a tool here. It says Add Point. I'm going to add a point here. And first I'm going to click on this corner of this lake. So this is the lake that exists here. It's called Al-Sur Lake. And I'm going to find this corner of these two streets. It's a fairly low resolution image, so we need to kind of zoom in and kind of approximately locate the corner. For this kind of georeferencing exercise, building corners, road intersections make good type points because they don't change as often over time. So do not use something that can be changed over time. Street intersections, building corners are a good reference. Once you click on a point, it gives you a pop-up saying, enter the X and Y coordinates. Now, we don't know the X and Y coordinates, but our map does. Our QGIS map knows exactly what the coordinates are. So I'm going to click this button at the bottom saying From Map Canvas. Once I get a pop-up, you can click this button From Map Canvas, and you'll be put back into the main QGIS canvas. You can now use the OpenStreetMap data and say, I want to now click on the same corner of that lake, which is where the two streets intersect. And if I click on it, you can see it has put in the coordinate of that particular pixel from the map in the CRS EPSG 3857. And this was done by clicking on the map. Okay, I'm going to show the process once again. First step, we select this tool. This is a Add Point tool, which is like a globe with a star on it. And I'm going to find a corner of this lake. I'm going to click a point here, and then click From Map Canvas. Go and find the same point on the OpenStreetMap base map that we've loaded and put it. It's going to add the coordinates. Make sure the CRS selector is EPSG 3857, since the coordinates we got are in the same CRS, so you can have that. So we have some editing tools available here. This is Add Point, Delete Point, and Move Point. You'll see the reference of this thing called GCP point. GCP stands for Ground Control Point, since they were in the olden times where we didn't have a base map. Imagine even 10, 15, 20 years back, we didn't have OpenStreetMap base map. We didn't have any base map where we knew what are the coordinates. So what you would do, you would go and collect those coordinates from your ground survey. So you go to the field and say, what is the coordinate of this corner? And that's why the name of this process uses this term called GCP, Ground Control Points. But again, we can use the GCP for this. I'm just going to do one more, and then we're just going to load the pre-saved points from there. So what makes other good points? Well, you can use some, this is a park to the south of the city. One of the things we want to do is we want to take points all across the map. If all our tie points are here, we don't know how to georeference it. So a good practice in georeferencing is to collect points at different corners of the map. So I'm going to go towards the south of the city, and you can see this distinct pattern. This is the botanical garden in the city. It's up to the south, and you can see if I zoom in here, you can see the same pattern here. So here is the pattern here. So you can click add point. I'm going to collect a point at this street corner here, pick from map canvas, and then I'm going to pick the corner of the map from here. And if you made a mistake, you can use this move point to move this particular point. So these are the two common points that you've identified. Do not worry too much about the accuracy, since this is a pretty old map, pretty low resolution. If you get it in the vicinity, it should be good enough. What we have done is we had taken similar points, maybe 8 to 10 points, and we have an option of saving the points. You can see there are buttons here. It says load GCP points and save GCP points. You can load this table of points that we have collected and save it as a file. We already have that file saved. So let's load those from a file that is in your data package. So I'm going to click this button. It says load GCP points. So find this button. It is the fifth button in your toolbar, which says load GCP points. In your data package, if you go under solutions folder, you'll find this file called Bangalore_GCP.points. This is the file which contains all the pre-saved GCPs. And try this out. Click the load GCP points button, browse to your data package. Under the solutions folder, you'll find this file called Bangalore_GCP.points. And you should, once you load this file, this is your pre-saved GCP that we had collected. You'll see some of the tie points that we have taken. Do not worry about where those points are, what those are. Few things to remember. One is you should have GCPs which are well distributed across your image. Do not collect all your tie points in a single region. Your georeferencing won't be that accurate. So ideally, one point in each corner will be there. How many points to collect? Well, that depends on what transformation you want to use. Let's see what are the different options that are available to us. We're going to open up the documentation from here. I've linked to this documentation from the course material. This is the georeferencing documentation. There are different kinds of transformations that are available. So remember, we are trying to assign coordinates to all pixels of our image. We can't collect coordinates of every pixel. We have just had some representative points. We say, I have 10 points. Now, how do I use those 10 points to assign coordinates to every pixel? There are different methods. You can see there are methods such as linear and Helmut, which says, give me 2 points and I'll shift your image. These are useful only for, they can only do scaling. So if you can have a big map, you can make it small. You can't apply any other transformation. For any kind of useful map transformation, you need to use at least polynomial 1 algorithm, where it says I need 3 GCPs. So if I have 3 points, I'm able to rotate the map, scale it, shift it, and then put it at the right place. So if you're, again, it says which transformations are useful for what kind of maps. Typically, if you have a digitally created map, a polynomial 1 algorithm might be able to fit it nicely. But if you have kind of hand-drawn map or map that has been skewed, you need to go to a higher level transformation. So we're going to try using the second and third degree polynomials, which is can apply some skewing to a map. That means if there's a straight line in your map, it can get curved. It can apply transformation to fit the map exactly. So let's try this polynomial algorithm and see how it georeferences our map. Back in the georeferencer, I need to go to the settings. So click this settings button. It says transformation settings. You can see we have different options for transformations. We're going to select polynomial 2. We'll try a few and see how the results change. For now, let's just use polynomial 2 as your transformation type. The target CRS is 3857. So that's where all our coordinates are. So be sure you select 3857. I will save it to an output file. So click this 3-dot button, browse to a location on your system. I'm going to just name this file as a .tiff file. It'll save it as geotiff file. So use that. There is some compression. Typically, these are all lossless compression, so don't change the data, but at least choose one of these. Unreferenced rasters can be very large, so you need to apply at least some compression to it. Deflate is a good choice. When you are transforming the map and you're creating new pixels, it uses some resampling method. In this case, we have a very low resolution image. Doesn't matter if you are working with a high resolution map and high resolution image, you should use bilinear or cubic, and that will give you a little smoother output image. But for now, nearest neighbor is a good choice. So we've done the transformation settings, chose polynomial 2 as our transformation type, 3857 as our target CRS. We assign the output file name and chose nearest neighbor as a resampling, deflate as a compression. Click OK. Once you choose transformation methods, you will see stuff here. Let me just go and explain how to interpret this table. What this says is we have a GCP. This is the pixel. So this is at the X pixel 220. So the pixels are counted from here. So you can say the pixel at the 222nd column and 431st row is this pixel. And this is the destination X and Y. So this is the coordinate in the 3857. Once we apply the transformation, it says we are trying to fit a polynomial transformation. Once we apply the transformation, this is the residual. That means when I fit the image and adjust everything, I have a residual of 0.04 pixels. That means I try to fit the point exactly where you asked me to, but I could not fit it exactly because I have restrictions. I can only use the second order polynomial. There are other pixels. For example, this one is 2 pixels error. I can right click and recenter to see where that is. If I see this one, you can see this one has moved. So it says you asked me to put this, assign this coordinate to this pixel. After applying the transform, this one moved slightly. That means the image, after we georeference it, it will shift slightly. It's not exactly very specified. And this happens because unless you have a perfect TCPs and a one-to-one transform, you'll have some residual errors. This is useful to identify outliers. Maybe you got some point really wrong. You put a point and you made a mistake. If you see a residual to be very high, 10, 15, 20 pixels, then you might think, oh, this is probably a wrong error. So either you can shift, adjust your GCP or just remove it. And that'll give you an idea of what is there. A few pixels error here just should be okay, it's acceptable. But again, this is what residual means. Your source pixel coordinate that you asked me to do. And then once you apply the transformation, it's going to adjust all the pixels. After adjustment, so we have configured our transformation settings. We know where the file is going. And if you're happy with this, let's go and run the georeferencing. Click the play button. There's a play button here which says start georeferencing. Once you run this, it's going to go through and assign the coordinate to each pixel of the image and create a geotiff file after transforming your original image and load it on top of QGIS. We'll run this. And now if I switch back to QGIS, you'll see your map overlaid on top of the OpenStreetMap base map. And if I turn this off and see, you'll see, you can compare the map, the georeference map with the base map. And again, just by the fact of that we could overlay this, we can now get so many insights out of this. You can now go to a place where you live and say, how did this place look 100 years back? And you can see what was there before. And you can see this is a stadium. And I have passed by the stadium many times. And I didn't know till I did this exercise that this was a lake before. This was a lake bed. And then, the lake was lost and now there's a stadium here. And so again, you can see how your city looked 100 years back by georeferencing data. And there are many such maps available. If you search archives, you'll find many people have scanned this, and you can find a map for your own region and try to georeference it. You can see the map overlays well. There's a slight distortion to the map that we could, we had a nice rectangular image. Once we transformed it, it has to warp it a bit to make it fit within the GCPs that we had chosen. You may get a more warped image or something. If it doesn't look good, few things to check. One, check your GCPs. You may have made a mistake. There may not be one-to-one correspondence. You may need to use the different transformation settings. There are different settings available. Depending on what you choose, you'll have more or less distortion in your final image. Let's try an exercise where you get to try different transformation on this data and see how the result changes. If you want to catch up to this point, you can load the project georeferencing checkpoint 2. So you have to go to georeferencing, open the 1924 image, load the GCPs, which is also in the solutions folder, the GCP points. And now you are ready to do the exercise. We have the image, we have the type points that we've loaded, and we'll try different transformations. One transformation that we want to try is something called TPS, thin plate spline. Remember when we had chosen these type points, we said use this as a reference and try to adjust and fit the map on the base map. But here we are saying that apply some transformation and try the best fit. We still end up with some errors. So for example, if you see here, each pixel may not be fit exactly where we have referenced it. There's a transformation called thin plate spline, which says use this as anchor points. Imagine a rubber sheet, and you say, I have a rubber sheet and I have these pegs. I'll try to fit my map exactly at those pegs. So I can do transformation. I can stretch and warp the image in any direction I want. And I'll fit the map exactly at those GCPs that you had specified. This is useful where your maps have very high distortion. It's useful for maps which are, or images which are non-orthorectified, which have terrain effects and so on, and you want to just fit them exactly with non-linear transformation. The thin plate spline is a good transformation. You can try this out. So let's do the exercise where you can try this algorithm on the same data and compare with the base map. Now you can explain the exercise.
So you may have the GCPs and we have the image, and we tried polynomial 2 transformation, and now you can just go to the setting and change this to TPS and just run the georeferencer and see what it gives. Have both the maps, you can save it as different image, so you can have both the image and visualize.
And you'll see there'll be higher distortion, but again, you can compare how rubber sheeting transformation works versus a polynomial one. And GIS people had to do a lot of georeferencing, and then we had good data available like OpenStreetMap and good base maps. People stopped georeferencing. Nowadays, people have started georeferencing again. The reason being, everybody wants to do machine learning. If you want to do machine learning, you need historic data. If you want to study, let's say I want to build a machine learning model to predict urban growth, well, I need to know how the city looked 10 years ago, 15 years ago, 20 years ago. And that's why GIS people now need to learn how to do georeferencing. I meet many people who are now doing GIS work and say, now we are spending time sourcing historic maps and georeferencing them. We're finding old reports and scanning those, getting those maps georeferenced so that we can build our machine learning models. So again, this is a skill that will come in handy, regardless of whether you want to use a historic map. Sometimes if you're working in a country, or the official data will come as reports or PDFs. You would not have a georeferenced data set available directly. So you would do you have to load a PDF and georeference it. So that's the life cycle of GIS. You create a map, export it as PDF, and then somebody will import this and georeference it. Hopefully we are out of this in many countries, but in still some countries, especially with historic data, we still have to do this and extract the data. If you had a map like this, let's say this is a georeference, sorry, it is a topographic map. So you can have historic topographic map. Many government agencies publish this. This will also come as images. They are not georeferenced map, but you can use this to extract coordinates. How would you do this? Well, most of them will have this coordinates marked on the map. So you can see this map grid here. And this map grid has those coordinates. So you can say I have this grid intersection here, and I know the coordinate of this grid intersection. I can read them from the map. And you can also use this to assign coordinates for a map. So I have a tutorial that shows how to do georeferencing by reading the map coordinates of a scan map. So for example, here we are georeferencing a map that looks like this. This is an old map, which has got grid lines. And you can see the grid line says this is 70-degree latitude, 75-degree latitude, 80-degree latitude, 15-degree longitude, 20-degree longitude, and so on. So I can say if I want to georeference this, I know the exact coordinate of this intersection. It is 15-degree latitude, 70-degree longitude. So instead of picking it from the map, I can say, I will put a GCP here and enter the coordinates manually, reading it off from the map grid. And this is a very easy way to do georeferencing, where you can just put a point and then enter that manually. So if I put it at a point, I can just enter the coordinates manually because I can read them off from the scan map. And once I have that map georeference, I know the coordinates of every pixel, and I can go use the photo and say, I can now see the same features as in the photo, and I can georeference that. So two techniques of georeferencing. One is if you have a map which has got grid lines, follow this technique. Or if you have a reference map like OpenStreetMap or Google Maps, and you can use some common features, you can go and pick the coordinates for the map. We're going to start working on learning how to edit data. And so many times when you're working in a GIS environment, you are working with the data that somebody created. So you download the data, you load it, and you start working on it. What if the data is wrong or incomplete? Let's say you got data about some railway stations or streets, and maybe one street is missing. How do you edit the data? How do you add that street? What if the name is wrong? How do you add the attribute? What if you don't have any data and you want to create it from scratch? So that are all the things you need to do and learn how to do data editing. So we'll learn how QGIS can be used for creating and editing new data set. QGIS has got really powerful functionality and not very well known. So we'll get a good preview of what QGIS is capable of. What we want to do is we have our georeference map. We want to extract and create a layer, a polygon layer of all the lakes. And we'll see how to do this. To start working on it, we're going to open up a project, not from the solutions folder, but from your data package. So we are now starting our digitizing exercise where we learn how to create new data using a reference map. Let's go to project, open, and in your main data package, introduction to QGIS folder, you have this project called digitizing.qgc. This is the starting point for this exercise. It is base map with the georeference map that we loaded, and we'll start digitizing data on top of this. Once you load this, you'll see that we have an OSM base map and our 100-year-old georeference map loaded on top of this. What we want to do is we want to now create a vector layer of polygons which represent each of these lakes. And we'll assign some attributes, and we'll use this to create a map of all the lakes that have been lost between these two eras. So what were the healthy lakes 100 years back and what were lost between this period. To create the data, we need to create a layer that we can add features to it. So first, let's go and create a new layer. We're going to go to the layer menu. So go to layer, create layer, and you have different options. You can create different kinds of layers. We want to create a geo package layer. When you're working in QGIS, a geo package is always a good choice. It's a lossless data format, a modern data format that can hold multiple layers. So unless you really need a shapefile, do not use it. As your data storage format, as your archival format, geo package is great. You can always export it as shapefile when you want to send it to somebody if they demand a shapefile. But for data storage, a geo package is a really good option. So let's create a new geo package layer. This is going to bring up a dialog where it's going to ask you to create a new geo package. Let's browse to, click these three dots, browse to a directory. It's going to name our layer as Bangalore_lakes.geopackage. So you can locate this file inside your data folder or anywhere on a computer that you need. Remember, a geopackage file can have multiple layers. So it says, what's the layer name? So we'll just still name it as Bangalore Lakes. Geometry type. We're going to draw polygons representing lakes. We could do polygon, but in general, when you are creating data set, multi-polygon is a good idea. A multi-polygon is a type of geometry where each feature can have polygons which can have holes or which can have multiple parts. And many features may need to be digitized as multi-polygons. So it's a good idea to always use multi-polygon as a data source. So in case you need to have a lake which is maybe separated by a bridge in between, and you want to digitize those two as separate parts, but as the same feature, you could do that. So let's choose multi-polygon as the option. We're going to keep the source CRS as 4326. 4326 is okay CRS for storing data. It's not a good CRS for creating maps, but for data storage, it's perfectly fine. So we'll keep that as the CRS. We have a layer. We want to create a layer of polygons for the lakes. Let's add some attributes. So when we create a layer, we can assign some attributes to it. The first attribute I want to add is called a name. So we'll add name of the lake, and so it's a type text and maximum length 50. So up to 50 characters of name it can hold. So let's enter this. So each feature in the layer should have a name. That's why we're creating a name column. Once you enter this, click this button, add to field list. So click it, you should see that option added on the bottom here, that this is a layer, has one field name called name with the type text and length 50. We also want to add one more feature where we want to name it status. So when we are drawing a lake, we want to store whether this lake is healthy or it's lost between this two era or it's partially lost. So we want to add some status information. So let's just add a new column which can hold the status. And we'll use some code. We'll say status is 1, 2, or 3. 1 is healthy, 2 is partially healthy, partially lost, 3 is lost, and so on. So let's just assign that as integer, 32-bit. So this column will just hold values like 1, 2, 3. So we can just use an integer value. And after that, also click add field to list. So now your field should have 2 values. So one is name and status. And once you click OK, you should see a new layer added to your layers panel called Bangalore Lakes. Let's right click and open the attribute table. You can see that this is a layer. It's an empty layer that we created. It's got 3 columns, FID, name, and status. We don't have any features because we not added it. So now we have an empty layer, empty geopackage layer, which has these 2 columns we created. All geopackages have an FID field by default, which is an auto-incrementing ID field, which is an integer 1 to 3 that gets assigned automatically. So we have our empty layer and we want to do some configuration. But before that, let me just show you what happens when you digitize a layer. I'm going to teach you digitizing step by step. So do not try digitizing yet, because I'm going to show you some configuration that we need to do before we start digitizing. Let's say we are drawing a polygon. Let's say I'm drawing a polygon for the lake. Just going to just draw this very roughly to demonstrate. Once I finish, it says enter some attribute. And I would enter some attribute. Say I'm going to just say lake A. Status, I need to enter 1, 2, or 3. That's how I'm designing my data schema. 1 means it's healthy lake. It was there 100 years back. It's still there. 2 means partially lost. 3 means it's lost. So if I enter 2, it'll indicate it's partially lost. Now this is kind of cumbersome for the user. I might also make a mistake. I have to remember the schema in my head and I might make a mistake. So what I want to do is I want to change this form that pops up once for entering the attribute. This comes up every time you draw a new feature. Let's say I'm drawing a new feature and I want to enter the attribute, this thing comes up. This is called an attribute form. And I can change the appearance of this and make it more user-friendly. How do we do this? Well, we need to go to the layer properties. So first, before we actually start drawing the features, we can go to the layer and configure our attribute form. Right-click the Bangalore Lakes layer, go to properties. In the properties, on the left-hand side, we have this tab called attribute form. Go and find that. And here we want to change the one for status. So select the one for status. Right now, the widget that comes up is a range. That means you can enter value like 1, 2, 3, 4, whatever. It's a free form. What I want to do is instead of giving the user a choice or myself the choice to enter anything and potentially make a mistake, I just want to add a nice drop down, which allows me to pick the status without remembering my data schema. A good way to do this is to change the widget type to be a value map. So go and change the widget for status. So we are in the properties of the Bangalore Lakes layer. Go to the status, change the widget type to be a value map. A value map allows you to create a drop-down value where you can say the user will get to see some value, and when they select the value, it'll correspond to a value in a data schema. So I'm going to fill this value here. I expect the data to have values like 1, 2, and 3 for the status. If the value is 1, that should be healthy. If the value is 2, that is partially lost. And status 3, that means it's lost. This is what I thought of how I want my data to be stored. Once I configure this, the user never sees 1, 2, 3. They only see this description and they can pick the one that makes sense. And in the database, it gets stored as 1, 2, 3. So it's a nice way for the user to pick a value without remembering the codes for different things, but your data schema still remains intact. So enter value 1, healthy, 2, partially lost, 3 is lost. We have some constraints. So when you are adding a new feature to our layer, we want all features to have a status. It may not have a name. Maybe we don't know the name of the lake, but we really want to enter the status. So we can say at the bottom, there's a constraint section. In the constraint, which says not null, means user has to pick a value. It cannot be null. And enforce not null constraint. That means do not allow addition of any new data if this value of the status is null. And this is a good thing to enforce for data integrity If you have a database, you want to make sure that people do not enter invalid values. So QGIS has many ways to enforce this. This is just a simple way to say, do not leave it null. Pick one of those values from here. Make sure you've done this configuration and click OK. We're done with this part. I'm going to show you what happens now after this configuration. What was the effect of this configuration? Now, when I draw a new feature, you can see my attribute form gives me a nice drop down and say I can choose whether it's healthy, partially lost, or lost. Right? It's a nice option. Instead of just a value that I need to remember to enter, I now have a drop down. And this was configured by us by changing the widget type to be a value map. Now you can pick healthy, partially lost, etc., and then you can enter that. If you want to catch up to this point, you can now load the digitizing checkpoint 1 project, which has got the configuration that we've done so far. So if you want to catch up, go to project, go to the solutions folder, and load the digitizing checkpoint 1 project. This will have the empty layer with the correct columns and correct configuration for our status column. I highly recommend is when you have a GeoPackage layer, the FIDs are very important to GeoPackage. Every feature must have a unique integer assigned to it as FID. GeoPackage maintains the FIDs by itself. So ideally, the user should not be able to edit FIDs. Right now, if I'm adding a new feature to it, you'll see that the FID field, it says auto-generate. That's fine. I want it to be auto-generated. GeoPackage will maintain that. But right now, I also have an option. I can say I'll delete and I enter some value. If I enter a duplicate value or something that doesn't make sense, my GeoPackage might get corrupted. So this is a very bad thing. So one of the things that you always want to do is you want to make sure that users cannot change your FID field. It should be auto-generated. And we'll learn how to do this as part of our next challenge. So let's see how we can set up our attribute form so that our FIDs are not editable by the users. Let's do the next exercise where we learn how to prevent FIDs from being editable by the user.
So you just saw how it is giving a user the privilege to, edit the ID, and we don't want that. So you can just go to your form, attribute form, and for your FID, you can find an option so that user cannot edit this particular field.
This will be our exercise challenge 4.1.1. Try this out. It's a simple setting, but very useful one. It's going to save you a lot of pain. Whenever you have a data that you are editing or somebody else is editing, make sure you lock this up, and FIDs should be auto-generated. GeoPackage is a great format. The only downside is the FIDs can be quite tricky. Sometimes when you do data merging or somebody changes FID to something, it causes all sort of complexities. So we should not be editing those manually at all. Even if you are doing some editing with GeoPackages, do not go and change the FIDs. Even if you feel that's a good choice, let the GeoPackage format handle that FID for you. We'll start the next section on digitizing polygons. We have a lake layer. We have configured it. It's a multi-polygon layer. We have added the two attributes, name and status, and we want to now add draw polygons. Before we draw it, we want to make sure we have our toolbar enabled. One of the toolbars we'll need for any kind of digitizing is the snapping toolbar. So we can go to View, Toolbars, and make sure we have enabled the snapping toolbar. If you see a toolbar with the magnet icon, you're all set. But if you don't see it, make sure you have that enabled. So go to View, Panels, and Snapping toolbar has to be enabled. Let's turn on the snapping settings. Click on the magnet icon. Snapping is when you're drawing something. If you're trying to draw a polygon, you want to close the polygon. You want to snap to the first vertex. You want to go and let QGIS allow you to drop a point exactly on the existing features versus somewhere close by. If this setting is not enabled, you might get open polygons or invalid polygons or overlapping polygons and so on. So make sure the snapping settings are enabled. There are some options. The default options are good enough. So just make sure the snapping is on whenever you are doing some digitizing. I'll explain the process of digitizing. First, we'll see which lake we want to digitize. So we have these two layers. This is the current map. This is a 100-year-old map. Let's say we are drawing polygon for this lake. We want to find out, is this lake healthy, partially lost, or completely lost? So in this case, This lake looks healthy. It was there 100 years ago. It still exists. So this current map shows the lake as it is. It was there. So when we digitize this, we'll say the status is healthy. If we are digitizing this lake, for example, this is a water body here. It doesn't exist currently. There's nothing here. So that means the attribute for status would be lost. So first, before digitizing, we'll just check the status of each lake, and then we can start drawing. Let's draw this lake first. Select the Bangalore layer lakes and click the pencil icon on the digitizing toolbar. You should have a toolbar on QGIS with a pencil icon. Click on that to say toggle editing. By default, the layers are not editable. You need to turn on the editing. So find the pencil icon and click on that. Once you click the pencil icon, the rest of the tools from the toolbars will get enabled. Go and find this tool. It says add polygon feature. Once you select this tool, your icon will change to be a different icon. And we can now hold your left mouse button, click a point, and find the next vertex you want to add. Click with the left mouse button and keep clicking and drawing stuff. If you make a mistake, for example, I added wrong vertex, the backspace key on your keyboard will delete the vertex. So backspace will delete each vertex if you made a mistake. You can then go and click different vertex at each edge that you want to digitize. Once you're done, right click will close the polygon. So you can see I'm almost there. I just want to enter the vertex at the last location. I can right click and it'll close the polygon. It'll give me a pop-up to fill the attributes. So the name, I can enter the name. If I can read from the map, if you can't read it, it's fine. You can skip it. Status, we have to give a status. This was a healthy one. So I'll just select healthy. And now I can click OK. And you can see now I have digitized this polygon. Try this process. I'm going to demonstrate this again with a different feature. If I look at my attribute table right now, you can see it shows like this. The edits are not saved to the file yet. They are still in memory. If I want to save my edits, next to the pencil icon, there is a button, Save Layer Edits. So keep saving your work. That means now it's written to disk. Next, I want to digitize this one. I'm going to see this is a lost lake that was lost. So I'm going to remember that. And then in the pencil icon, enable that. And then I'll add polygon feature. Left click to start the polygon. Keep clicking your left mouse button and drawing the polygon. Backspace to delete the last vertex. And keep digitizing it. Right click to finish the polygon. Name, I'll leave it blank. And this one would be lost. You can enter the attribute according to the status of the lake. Try this out, practice adding a feature, try at least a couple of them. You don't need to be very precise for this. This is for learning how to do this. When you are doing this for real, you may want to zoom in, use your scroll wheel to make sure you are drawing it exactly. If you made a mistake, for example, if I've done digitizing and I want to edit the polygon, I can use, there's a vertex tool here. You can select a vertex tool. If I hover over a feature, you can see I have different vertices. I can go click on a vertex and move it. So this allows you to adjust the polygon after the fact. This is super helpful when you caught some data, and maybe one or two features are wrong and you want to reshape them. This is the tool that you'd use to move certain vertices that you need. We're not going to digitize all the lakes. We don't have a few hours to do this. We've already done this, but I want to demonstrate a few advanced things for digitizing. One thing about multi-polygons. Let's say we have a lake like this. Let's say we want to digitize a lake like this. We have a road passing through this. So the lake feature it's a two-part feature. I can't digitize a single feature because it's in two parts. There's no lake here in between. So I want to digitize this as a multi-polygon. Let's see how to do this. Again, look at this. I want you to understand the concept and what are the tools available. You can practice it later on. We'll start digitizing. We'll digitize the first part. So I'm going to say this is the first part of that same feature. I'm going to digitize this. Okay, so now what I want to do is I don't want to create a new feature. It's the same lake, but it's called polygon is split into two parts. So I want to add a new part to this particular polygon. That can be done by the advanced digitizing toolbar. So I'm going to enable one more toolbar, view toolbar, advanced digitizing toolbar. This has got some advanced features. I'm going to show some of them so you understand what it does. Again, you can see this pops up so many new tools here. I'm going to select this feature and then I want to add this tool, add part. So add part is I have a polygon feature. It's a multi-polygon geometry. So I have one part, I want to add second part to it. So I'm going to draw this and now I'm going to digitize the second part. We'll save this. And now an important thing to understand. If I select this feature, you can see it selects both the parts. If I look at the attribute table, there's only one feature. It's not two features, it's just one feature, but the polygon has two parts to it. And this kind of data can be represented only by a multi-polygon geometry. This is what we mean by multi-polygon. A polygon can have multiple parts to it. Let's say we want to digitize this lake, which is called islands. I want to have water, but I need to have holes in it. How do you digitize that? Again, this is a demo. You don't need to do this, just to show how one can digitize features like this. So first, I'll digitize the outer polygons. Now I want to have the hole in between. So I can say there is an option, add ring. A multi-polygon can have a ring. A ring is a polygon can have at least one ring. You can, as you add a ring, the inside ring will be considered as hole. So I can now say I have this ring. I want to select this and then say add ring. And then as I add a ring, you'll see that now this polygon is digitized with a hole. So you can have multi-polygons where it's a polygon with a hole, polygon with multiple parts, or both. And this is what the multi-polygon geometry allows it. I'm going to load the checkpoint project. If you practiced a few polygons, got used to the process, that's good enough. Let's see what the final layer for this exercise looks like. I'm going to go to my projects and the solutions folder. And we'll load the digitizing checkpoint 2 project. This has all the lakes been digitized. If I open the attribute table, you can see we have added the attribute of all the lakes. Some of them have names which we have added. Some of the names are not known. So you have it this as null. You added the different status to it. And now we have created a data set from scratch. Remember, we didn't have any data. We just found some map, georeferenced it, extracted the features, created this, and now we have a really useful data set, which we can use to figure out which lakes were lost, how many square meters of surface water was lost, and so on. So let's load this checkpoint 2, and then we have an exercise to create a map from this data set. Now you can explain the next exercise. This exercise is best done using the checkpoint project. So if you want to use your project, make sure you can save it, but then load the checkpoint project so you can do the exercise unless you were super fast and could digitize all the polygons in the short time you had. Then use your stuff. Otherwise, use the one from checkpoint.
So for this challenge, we want to see these lakes based on its status. You see the healthy ones are dark blue, partially lost are light blue, and the ones which are lost are in the red colors. So here you see that we can do this using the categorized symbology. So you can try in the symbology panel, try categorized option, and then you can have these 3 categories using the column that we have, which is status. So use this categorized option, select the column status, and you will see that you have 3 categories. You can change colors according to your choice, but it should have these 3 categories and it should look like this.
So we'll explore the new symbology, which we haven't tried yet. We have tried single symbols. We've tried graduated. This time, let's try the categorized symbology where you can assign color based on the category of the value. So let's try the exercise for section 4.2.1 and create a map like this. One of the most important data set that emerged in the last decade, and it's a must-have for all the geospatial data scientists, is OpenStreetMap. It's an amazing database. It's a free and open map of the world created by volunteers and many companies who are contributing this data to this amazing map, which is not only gives you this base map that you can use as a reference, but also it has got data on almost all roads, all the buildings, and all the different points of interest across the world. And you can use this data in your project. You can download that as vector data. So it'll be really important to understand some concepts around OpenStreetMap. If I go to openstreetmap.org, this is the map that you see. It's a global map. It started out as a project in the UK where they just wanted to create a free and open data set that anybody can use and build upon. It is now spread across the world where you have detailed street level maps for many places in the world. And if I zoom into a layer, you can see, if I zoom in, there's so much detail here. I have all the streets. You can see there's a name of each street. There's a direction. I have each building footprint. I have names of the building. I have all the POIs. You can see I can see all the restaurants here and a bunch of different things. Everything I see on this map can be downloaded as point lines and polygons, along with all the attributes. And I can use this in my data. This database has so much information. Only, I would say, half of it is shown on the map. But there's so much other information that consists of this database. And all of that can be downloaded and extracted. Let's say I'm working on a project. I want to say, I want all the EV charging stations in my city. I want a point database of that. I can download it from here. I want all the restaurants as POI, I can download that. I want all the building polygons in my city, I can download that. So first, let's understand how does OpenStreetMap store this data, and then we'll learn some of the tools in QGIS that allow you to download and use the data in your GIS project. We'll go through a short presentation here. You can kind of think of OpenStreetMap as Wikipedia for map. It's a collaborative project where volunteers come in and they add features, they edit features. They have a strong review system where you do an edit, you're a new user, your edit gets reviewed by somebody else. You can review somebody else's edit, and it's a kind of peer review kind of system, which allows you to have this high quality database. The OpenStreetMap is going to be a very big project. Also, it is many times it's often updates are faster than competitors because competitors have to go through, it's a centralized project. So somebody in a company needs to know there's something changed in the world, versus on OpenStreetMap, as a user, you can say, oh, the street became a one-way street. I can go and update OpenStreetMap. And then every user of OpenStreetMap has this information, they can use that. It is mostly created by volunteer mappers. There are multiple teams across the world. There are local OSM teams which have hackathons, mapathons. They create maps for the regions. They have specific teams that get activated when there's a disaster. So if there's a cyclone or there's a natural disaster, the teams go and map those regions as well. In recent times, there are many companies who have joined forces with OSM and they contribute data back. These are the companies that are interested in having a mapping product, but they've realized that owning and maintaining a mapping product is very hard. It's very expensive, it's very hard. Only a couple of people in the world have their own map data, Google being one, Apple has their own map data. Other people, it costs them billions of dollars to create that. Instead, they say, we'll use OSM. We'll contribute whatever we can, whatever our data back to OSM, and we'll use the data, OpenStreetMap data, to have a mapping product. Some of the main partners that OSM has are companies like Facebook. Facebook, if you go to facebook.com, use any of the map, they are all OSM maps. Facebook is really interested in knowing where people are, and they have a lot of data about people. They contribute our data back to OSM. Microsoft is also another partner. Amazon is interested in delivering packages. They want to know where all the pathways are, where all the houses are. They map and contribute a lot of data. Many ride-sharing companies, Uber is again a big partner of OSM. They have fleet on the street which are driving. They get the data, they contribute it back to OSM. Tab is another partner of OSM that they can do this. In a single day, in OpenStreetMap database, there are many, many changes, hundreds of thousands of edits that happen. And that means there are new features being added, plus existing feature being updated. There was a new road. It got detected either by an automated algorithm or by a human that got changed. The new restaurant got added and they get added. There are automated systems that Facebook has, which can detect roads from satellite imagery. They create those, then human reviewers review those and add it back. Microsoft has a pipeline for generating building footprints. and those can be added to OSM as well. Just want to open up this page to show you how active the project is and how rich the database is. It says in the last 60 minutes, there were more than 125,000 edits to this map. Can you just imagine the scale of the project? And there are dashboard versions where you can see in real time what people are editing. So I highly encourage you to participate. If you have a local OSM chapter, go to the meetup. They usually organize some mapathons where you can meet other users and participate in that. As a GIS user, we are also interested in using the OSM data, but OpenStreetMap uses a database to store the data. And as GIS people, we understand points, lines, and polygons. The OSM data model is very different. The terminology is very different than what GIS people use. So if you want to get data from OSM, we need to understand how OSM stores and processes the data. If you go to OSM, you might see certain nodes. So points of interest, shops, restaurants, railway stations, bus stops, all of those are represented as nodes. So if you want to download a point layer of all the bus stops, you'll say, give me all the nodes which are tagged as bus stops. OSM also has something called ways. Ways is like line segment. So roads, rivers, they're all ways. So if you want to download all roads, you'll say, give me all the ways which are of type, highway. Interestingly, buildings are also ways. So if you want to download all buildings, OSM says, oh, buildings are nothing but closed ways. So a line which is closed is a way. So this is a big difference. OSM doesn't have polygons, it's got ways. And the third thing that it has is something called a relation. A relation can be thought of as a virtual data type which can collect different things. So for example, a bus route. A bus route is not a physical thing, right? But it's, you can say a bus route 12 goes through this many bus stops, which are nodes. So a bus route could be a relation between different nodes of bus stops. And in OSM, they are represented as relations. If you have multi-polygon, we just saw that we can have a polygon with a hole. What is a multi-polygon? It's a polygon with two rings, an outer ring and an inner ring. So in OSM, it says this is a relation with an outer way and inner way. And that creates a relation which is multi-polygon. So polygons are ways, multi-polygons are relations in OSM. Other things like I have a bridge which is on a highway. So I have a bridge segment, I have a highway segment. There's a relation saying that this bridge is on this highway. So again, those are stored as different things. So depending on what you want, you may have to restrict your query in saying, I want only nodes, or I want only relations, or I want relations of this type to extract from OSM. So this is the geometry. So points, lines, polygons are nodes, bays, and relations. What about attributes? GIS data also has attributes. In OSM, those are stored as tags. So your attribute table will be stored as tags. So you can have a road segment and say, this is a segment where the highway equals motorway. So that means this is of type highway and the value is motorway. These are different kinds of road types in OSM. So if you see a road segment, this is highway secondary. That's a secondary road which is drawn in OSM. Some of this terminology may seem odd to people in the US or the rest of the world because OSM evolved in the UK, so they use all the UK terminology. So you might say, what is interstate highway tagged as? Like in the OSM documentation, it would say interstate highway would be tagged as a trunk way or a motorway, for example. We're going to learn about tags. There's a really nice documentation which says what are the tags for different types of commonly used data set. Let's say I want to download all hospitals. What is a tag for a hospital? And you can go and find those tags and download the data for the specific tag. How do I get OSM data? There's a plugin in QGIS called Quick OSM, one of my favorite plugins, which allows you to download data directly into QGIS. We're going to use this in this course where we'll specify what data we want, what region data we want, click a button, it downloads everything as a vector layer in QGIS with attributes and geometries. It auto converts all the nodes, lines, nodes, ways, and relations into points, lines, polygons, converts all the tags to a nice attribute table, and you can just start using your data. This is useful where you want to download data for an entire city or maybe for a country, but for a specific theme. If you want to download large amounts of data, this is not suitable. Let's say I want to download all roads in Germany. Well, you don't use this because it's going to take a long time. It's a very large query. It may fail. So for small, medium-sized data set, you can use this. There's a website called Geofabric, which does daily exports of OSM. It takes the old OpenStreetMap database, converts it to shapefiles every day. And you can download the latest shapefile for each country from this website. So you can say, I want to download everything in Germany. You go download, you'll get a few gigabytes of file, which has got all OSM features in Germany downloaded as a shapefile. So if you want country level data, you can go and download here. There are many other OSM exporters. There's also Interline, which allows you to extract city level data as GeoJSONs. I mostly end up using either of these two. If I'm doing some country level analysis, I'll use this website. If I'm doing city or regional level analysis, or even countrywide, I can say I want all EV charging stations in UK, which was a query I ran recently, and it works fine. So you can use this as a starting point and use this if you want all the data. I'm going to quickly show you this website. This is the Geofabric data. You can go and find the data for your country. Let's go to, say, I want to download stuff for India. So India is quite big, so they split this into different regions. You can go, say I want all the data in the central zone. I can download this as a shapefile. And I'll get shapefile for roads, POIs, water bodies, rivers, everything, all the things that OSM has. Again, OSM has so many things that this will give you most of the primary things like building footprints, roads, rivers, etc. But if you want a very specific thing, which I want all bus routes, this won't have bus routes. You will still have to query using the Quick OSM. Quick OSM allows you just to query for any specific tag or specific relation that you want. You can use this. So for generic mapping data, you can use the shapefiles. For querying a specific data, you can use the Quick OSM plugin, which we'll learn about shortly. If you're working with OpenStreetMap, do bookmark this page. This is one of the most useful pages in OSM. This has got listing of what are the different things called in OSM. It's a very big page. Let's search for, I always search for stuff here. So let's say I want to download hospitals. It says amenity equals hospital would give you all the hospitals. It's got some representative images and say, if there's a hospital, it is tagged in OSM as amenity equals hospital. And I can get all the hospitals. There are different kinds of things. There's a nursing home. I found nursing home. You can say amenity equals nursing home. Amenity equals pharmacy will give you all the pharmacies and so on. If I want airport, let's say I want to download polygons of all the airfields, locations of all the airports in a country. The tag is aeroway equals aerodrome. You can see this one can be a point or a polygon. So an airport could be just the polygon for the entire airport region or just the point at the center of the airport. So you can download either of those. Very useful, for example, if you want just all the taxiways of the airport, all the terminals, you can just get runways. If you just want polygons for all the runways of all the airports in your country, a single query and you'll get those polygons along with those attributes. So super helpful. So whatever data set you want, which is listed here, you can go and download it from OSM. So think about what data you need for a project and find it on this page here. Then in the next section, we'll learn how to query and download that directly into QGIS. We'll start on our final module of the course, geoprocessing. Geoprocessing refers to doing analysis, taking your data and working with the data, combining different data layers to analyze them and do some spatial operations on them. Where the question that we want to answer is, in a given city, we have a global data set of OpenStreetMap. We have also a global data set of population. So we can do this for any city or region that we want. For this, we're going to pick one city where we have already downloaded data for. In this city, how many people have equitable access to public transport? That's a question we want to answer. So we say, this city has a metro system. How many people live within 1 kilometer of a metro station in the city? And this is quite helpful when, as an urban planner, you want to design, maybe plan a new station or want to understand whether this metro system really serves people or not. So for that, we need first data on where are the metro stations in a given city. Once we have the metro station, we need to figure out what is the region around 1 kilometer. For that, we can define this multiple ways. We'll first do it in a simple way. We say we'll take a region and say we'll do a buffer around 1 kilometer. And that's a region around a metro station. So if you live within that buffer zone, you have a good access to your metro station. We can also do a little more smarter analysis where we can say how many people live within 1 kilometer of a walking distance. So we can take the road network data and compute real isochrones and say how many people can walk to a metro station within 1 kilometer. Once we have that, we want to know in that buffer zone, how many people actually live there. So we need some population data. And we'll have an overview of all the different population data sets that you can use. And once we have that, we need to count how many people live in the buffer zone. And then we can determine how many people have good access to metro station. And again, you can extend this analysis to bus routes and other transport system as well. So let's get started. First, we need to get OpenStreetMap data. So we're going to switch back to QGIS and we're going to start loading some data. Let's go to our data source manager. We're going to load vector data of the boundary of the city. So switch to the vector tab in the data source manager. Click the browse button, and in the introduction to QGIS folder, we have this file called bangalore.json. This is a file in the GeoJSON format. This is a very popular vector data format that is useful for doing web maps. So many times if you go and download some data, it might come as a GeoJSON file. And QGIS can just load it directly. You don't need any extension or plugin. It's just a vector format that QGIS supports. You can directly load that. So let's open this and click add. This is a single polygon showing the municipal boundary of the city. We're just going to use this as a reference to say, this is the city boundary. We'll count how many people live within that. And then once we get our metro network, we'll say how many people live within 1 kilometer of a metro station. And what is the percentage? Do 10% people live within 1 kilometer of a metro station? Is it 20% or so on? We can compute that. This also serves as a boundary for us to get the data. We can define to say, I want to download data within this boundary. If you're doing this for your own city, you can load a polygon boundary, or you can just use zoom into the region and download data for that. I'm also going to add a base map layer just for me to know, again, this boundary is optional. It's just for us to visualize the city boundary. To download data for any region from OpenStreetMap, you don't need this. You just need to know where you are. So to know where you are, you can just add a base map. I'm just going to go ahead and add the OSM base map. So go to your quick map services, OSM, and add OSM standard base map. We're going to use the plugin called Quick OSM to download data from OpenStreetMap. Let's go and install the plugin. If you have already installed it, it should be good to go. If not, you can search for the plugin called Quick OSM and make sure you install it. We will get some data. For our analysis, we need the data on the metro stations in the city, and then we can do the analysis. Before we download that, we're going to spend some time learning how to use this plugin and download all kinds of data from OSM. So we're going to learn how to refer to that wiki page with all the tags, and then how to use the OSM plugin to download the data that we need. Install the Quick OSM plugin. You will find this under the vector menu, Quick OSM, Quick OSM. So this is the main entry point for Quick OSM. It'll be under vector, Quick OSM, Quick OSM. Once we start the plugin, you'll see a window like this. And this is the main window, Quick Query, where we can define what we want and we can download data from it. If you open the Quick OSM from vector, Quick OSM, Quick OSM, and you'll see this window. Before we get our metro station data, let's try and understand how this works. And I'll do a demo of downloading different kinds of data. So again, you don't need to do anything. Just take a look, understand how this plugin works, how OSM works, and then we'll go ahead with that exercise. So a bit of detour to understand this Quick OSM plugin. All of the tags in OSM, where each feature is tagged with a specific information, those are available here on this wiki page. It's a very big page. You can search for different things. Let's say I'm doing some analysis for healthcare in the city, and I want to download all the healthcare facility in the city. It's a painful task if I want to go and manually collect it, but since OSM already has it, I can just use OSM, Quick OSM, to download data from that. First, I need to find out what is the hospital's tag. So I can just search for hospital, and it says all the hospitals are tagged with this tag, amenity equals hospitals. So if I search OSM for amenity equals hospital, I'll get all hospitals. Let's try this out. So in quick OSM, I'm going to come and say, what's the key? I'll search for the key is amenity, and the value is hospital. So now it says, I want to query for all features where they are tagged as amenity equals hospital in. I can search for the city name. The city name has to be the one how it has to, OSM should know that city name. So in Bangalore is a city that OSM knows about, you can do this. Or if I don't know the city name, I can just say in canvas extent. So zoom to the region and just say whatever is in this viewport, download all hospitals. For now, I'm just going to just say in Bangalore. And now I can just say run query. It's going to send you the OSM server. It's going to extract the feature that we want, convert it to a vector layer, and send it to us. You can see my query finished. I get points and polygons in QGIS. These are all the hospitals that OpenStreetMap knows about. And it's just not points. I can open the attribute table, and you can see they are all nodes. So this is how OSM represents points. I have all the names. So I know that this is the name of the hospital, what's the type, the local name, and so on, address, and all the things that OSM knows about. I could download that. And suddenly I have all the hospitals in the city. I have 800 plus hospital locations in my city as vector data. I can start analyzing it. And this works in any city. I can go to any city and say, give me the data, I can do this. What are the other things you can get? Well, let me just zoom into some region. You can see the OSM map is so quite rich. It's got so many information there. I would like to get all the building polygons. Maybe I'm doing some analysis. I want to know which are the more dense regions, and I'm doing some analysis. I want to get those building polygons, building footprints. So maybe I just want to get everything in this viewport. So I'll go back to my quick OSM, and I'll just say building. You can get specific type of building. You can say, I want apartments, I want church, I want farm, etc. You can leave it blank to say query on all values. So I want all buildings. I could also do in Bangalore, it'll get me all building footprints in the city. It might take a few minutes. Instead, I would just say in my canvas extent. So wherever my canvas is, I want all building within that region. And I can just click run query. And now I have all polygons, all building polygons as polygons, along with all the attributes of that building. So if the building has name, type, all of those are there, and I have those available to me. And this works again globally. Anywhere in the world, you can go and you have the starting point. Pretty amazing if you think about it. Just a few years back, we didn't have access to such data. Now you can, when working on a project, go and download all possible data sets, and then you can start using this. Finally, maybe we'll do one more. Let's say bus stop. I want all the bus stops in the city. It says highway equals bus stop are all bus stops. So now I can say I want to get all the bus stops in the city. So I can go back to quick OSM and say my key is highway is bus stop. And in, I would say Bangalore. And now have all the bus stops in the city. OpenStreetMap data is quite rich in many parts of the city. Even if it's not complete in your city, this is a great starting point for a project. So once we have our quick OSM installed, let's now go and download data for analysis. We want to get the data for all the metro stations in the city. So let's go to vector, quick OSM, quick OSM. You can now open the dialog so we can run the query. In the quick OSM dialog, you should be in the quick query tab, and we're going to search for all the metro station. They are tagged as railway station. So go and enter this key value pair. All the metro stations, also the intercity rails, etc. All of those are tagged as railway station. You can find what are the tags in the OSM wiki page that we mentioned, but for metro station, they are all tagged as railway station. For the region, we can say the map canvas. So if you're zoomed into the region that we want to download for, we can use this. Or in this case, we're just going to type Bangalore. It's Bangalore, Bangalore. Many of the metro stations are drawn as both points and polygons. So you have a metro station, you'll have actually a station geometry. For our analysis, we're just looking for points. So we'll restrict our query to be only points. So once we run this, don't click run yet. Expand the advanced section. In the advanced section, you'll have certain types of data. So what kind of data you want to query? We'll uncheck everything except node. So we don't want any ways or relations. We don't want polygons. You only want points for the stations. And similarly for the geometry type, we only want points. So in your configuration, make sure you have put key is railway, value is station. In Bangalore, the spelling of Bangalore is Bangalore. In the advanced section, uncheck everything except node and points. Once you've done this configuration, you can click run query. It says query successful, one layer has been loaded. You can change the order. I'm just going to make it on the top. And you can see I have a points layer which got loaded. This is the result of my query from OpenStreetMap. These are all the railway stations in the city. It's not yet only metro stations. It's all the railway stations in the city. The city also has some intercity railway systems. So this includes stations for that. So we're going to make sure we get only that, but this is a good starting point for getting all our railway stations. Let's open the attribute table. So I'm going to select the railway station Bangalore layer, right click and open attribute table. This shows all the attributes that are there in the OSM. We have the name of each railway station, both in English and the local language. We also have the network. So the network is the operator who operates this railway. So the metro operator is called Bangalore Metro Rail Corporation Limited. So this is the operator who operates the metro. There are other intercity trains which are operated by Southwestern Railways. So there are two different systems here. For our analysis, we are only interested in the metro line. So we want to say, show me the stations which are part of the metro, which are operated by this particular provider, this particular operator. We can apply a filter to see only the points where the operator is equal to this particular operator. Let's close this attribute table. I can apply a filter. So right click and select filter. The filter dialog, we only want to select railway stations which are operated by the metro operator. So I'm going to say the field would be operator. So I'm going to select double click operator as the operator. I can get all the values here if I select operator and click all. So these are the different operators. So I can say operator equals this operator, Bangalore Metro Rail Corporation Limited. You can just pick the string from here. So this will be our query. Wherever the operator field value is equal to this string, then only the feature will be selected. So from the field, you can scroll down, select the operator, double click it to add it to the query here. Click all to get all the values of that in the data set. Double click this to enter this here, and you can add an equal to sign in between. Now you should see a subset of the railway stations. And for me, it looks like this. And if you're familiar with the city, you can see this looks like the metro line. This is the north-south line, and this is the east-west line. So these are currently two operational metro lines. So now we've selected only the metro stations which are there in the city. You can also see there's an active filter being applied here. The metro line is actively under construction in the city. So at a later point, when you run this query, you might see more metro stations. And every month they're opening a new metro station. So you might see a different map when you do the query at a later stage. But again, at this point, this is the current metro network. When we add query and add data to OSM, it assigns some colors to it. Here it is figured out, it is assigned two different colors. We don't want that. We just want everything to be in a single color. This is just a styling that Quick OSM plugin applies. Let's just change it to a single symbol style. So I'm going to click this paintbrush icon to open the layer styling panel. And we're going to change it from categorized to single symbols. And now you should see all the stations in the same color. So this is the data set. We are now going to use this and analyze how many people live within 1 kilometer of this metro network. You can see that this layer is currently still a temporary layer. We have applied some filter, we have changed the styling. Let's save it to disk. Whenever you have a layer which is temporary layer, It means that when you close QGIS, the layer will go away. So we want to save it to disk. We'll save it as a geo package. The easiest way to save it when you have a temporary layer is to right click and say make permanent. So right click the railway station layer and select this option, make permanent. It's going to give you an option. Make sure the format is geo package. You're going to save it as Bangalore underscore railway underscore stations or railway stations Bangalore. And once you have it, click OK. This will go ahead and save that layer on your disk as a geo package. This layer now exists on my file system. It won't go away when I save it. And we are done with the first part of exercise, downloading and cleaning up the data from OpenStreetMap. You can go ahead and save your project. If you want to catch up to this point, you can load the Checkpoint 1 project. So I'm going to go and load the Checkpoint 1 project. Remember, the Checkpoint 1 project was saved a few months earlier than current. So there are fewer metro stations in the Checkpoint project. So do not worry if your map and my map looks different. You can continue using your data set, but I'm going to load the Checkpoint 1 project. So I'll show you what that looks like in case people want to catch up to that. This is going to be the Geoprocessing Checkpoint 1 project. And this is what the current Checkpoint project looks like. As I mentioned, the Checkpoint project was saved a few months ago. That has fewer metro stations. Doesn't matter for the purpose of this exercise. If you have saved your project, you can continue working on your project. Let's do the next challenge. So now you're ready to do your next challenge, which is the challenge 5.1.1. We have this OSM data layer that we have downloaded. You can see that we have so many attributes here. And it's not, we don't need all of that. All we need is the ID of the feature, because since we are just going to do a buffer analysis, we don't even need to know the name, etc. So let's learn how to clean up our attribute table. So the challenge is we want to take our attribute table and delete all columns except the ones that are named FID and OSM ID. You can go and delete all of the other columns. You can see there are some hints given here. You can try this out and see if you can clean up your attribute table to have only these 2 columns, delete everything else. We're going to do the next part of our analysis where we need to now compute how many people live within 1 kilometer of metro station. We know where the metro stations are. We need to now figure out what is the buffer zone of 1 kilometer around that. So we're going to start on the next section, section 5.2 from the course material, where we'll compute the 1 kilometer buffer. I'll explain some of the concepts here, and then you can start doing this on your side. First, how do we compute a zone of 1 kilometer buffer? We have a tool called buffer in QGIS. I'm going to go to processing in toolbox, search for the buffer tool. And I found this tool here under vector geometry, buffer. I'm going to open that. I want to compute a 1 kilometer buffer. If I try to do it here, it says how much distance you need. And what do I specify here? I need 1 kilometer, but my unit of the CRS, my data is in 4326, it's in lat long. So the only option I have is degrees. So what do I specify here? I can't compute buffer in degrees. There's also a big warning here saying that distance is in geographic degrees. That's not right. You cannot compute distance in degrees. You have to change your projection to be in a projected CRS. So again, before even we can do buffer, we have to reproject the data to a projected CRS. So we can't do buffer yet. We need to change our CRS to something that has distance unit in feet or meters. What CRS to choose? Well, it depends on your region. If you are in a region which is called official CRS that is used in your region, use that. If you're in a region that doesn't have CRS, if your city or region doesn't have a CRS, a UTM is good CRS. So UTM is a coordinate system where you have a 6-degree zone. The whole world is divided into 6-degree zones, and you can pick a UTM zone where your city falls, and that will give you the highest accuracy within that region. How do I find out what's the UTM zone? There is a handy tool that you can use. This one is a tool that says which UTM zone am I in. So you can see these are the UTM zones of the world. If I click on a polygon, it'll show me that this is the UTM zone 53. I need to find out where my city is, and I can find out the UTM zone. So for here, the city of Bangalore is here. So I can click here and say, what UTM zone does Bangalore in? And this is UTM zone 43. Each UTM zone also has north and south. If you're above equator, it'll be in north zone. If you are below equator, it'll be in south zone. So pick a UTM zone for whichever city that you want to do analysis on. Let's say if you want to analyze some city, you are doing this analysis for Lagos, then you'd come here and say, what's a UTM zone for Lagos? It's UTM zone 31 north. And you'll pick a CRS for that. So we're going to reproject the data to that CRS. So I can now use meters as units. So we're going to go to reproject layer. You can do this now along with me. Select your railway stations Bangalore layer. Select the reproject layer tool and double click to open it. Here, our target CRS means to specify the UTM zone 43 north. Here's a CRS selector button. So in the target CRS, click this globe button, which says select CRS. We need to pick the CRS that we want to reproject to. And we're going to filter it for UTM zone 43 end. So I'm going to search for this keyword, UTM zone 43 north. And here, if I expand this, this is going to show me all the matches that I found for UTM zone 43 north. As we learned in the introduction to GIS presentation earlier, that there are different datums on which you can create this UTM grid. The datum that we want to use is WGS84. This is the most modern datum that is globally applicable. So we're going to pick the CRS, which is the UTM zone 43 north CRS based on the WGS84 datum. You can also, if you know the EPSG code, you can search for EPSG code 32643 and you'll hit this CRS. So make sure we have chosen this CRS 32643 and click OK. So our target CRS is 32643. And finally, for the output layer, we're going to save to a file. We're going to name this file Metro Stations Reprojected. Once you're done, click Run. And you should have another layer on your QGIS named Metro Stations Reprojected. This is the layer that we want to use it from now on. This is the one that is in the CRS 3264. Once we have this reprojected layer, we can try the buffer. So let's do a buffer of 1 kilometer. Once we have the reprojected layer, let's try buffering now. So I'm going to open the buffer tool. Now you can see we have an option to select a distance unit. Because we have projected layer in the projected CRS, we can now compute distance in linear measurement unit. And this is a very important thing. Do not use degrees for your buffers. You need to have a projected CRS. Let's do a distance of 1 kilometer. So make sure you change both the distance to be 1, the unit to be kilometer. I'm just going to show you what happens if you just run the buffer like this right now. Do not click run yet. Even if you configure it, just hold it like this. I'm going to run this and you can see you get buffers. So you now get a buffer, 1 kilometer buffer around each point. That's great. But we get individual buffers. We get this overlapping circles, which we don't want. We only want to know all the region around a metro station, which is 1 kilometer. So what we want to do is we want to merge all these different polygons and create a single polygon out of this. So for that, we have an option in the buffer tool. I'm going to go back to the buffer tool and say, I want a 1 kilometer buffer. But now there's an option dissolve result. A dissolve result will just merge all of those resulting buffers, give you a single polygon. So make sure you click the dissolve result and save our output as metro station buffer. So now we have configured a tool. Make sure you configure it like this. Once you're done, you can click run. So now we know where people live, where you can live in the city and be within 1 kilometer of a metro station. So we have a buffer zone. We're ready to count the population. We just have one problem though. We're going to use some population data set. The population data set we're going to use comes in the coordinate system 4326. This comes in EPSG 4326. So if we are trying to extract population within this buffer zone, there's a mismatch in the CRS. This one is right now in UTM, that one is in lat long. We have to match one of them. So either we can take the raster, reproject it to UTM, or take this buffer zone and turn it back into lat long, since we have to match the projection of different layers before we can extract the data. So for many projects, you should be working in a project CRS from very beginning. So we'll just get all the data reprojected there. For this project, since we had to use the projected CRS only for buffer, we can switch back to 4326. So we have a buffer now. Let us reproject it back to 4326. So we can now use other data sets which come in 4326 and we can combine them. Either is fine. You can keep this CRS and reproject your raster in the next section, or we can reproject this to match the raster CRS. It's easiest to just take this and turn it back into 4326. So we can do this now. So I'm going to do a reproject layer again. So I'm going to click reproject layer. We have a metro station buffer, which is in 32643. We're going to turn it back into 4326. And we're going to save the output as metro station buffer. Reprojected. This is just an additional step because we have different layers in different CRS. If you want to merge them or do some analysis with them, we have to match the CRS. So again, your choice. If you're doing an analysis that doesn't involve distance units, you can turn it back to 4326 and then continue. If you want to do more buffers or other distance-based analysis, make sure you project everything into a UTM and then you can use that. Let's do this. And I'm going to run this. This will be the final layer for this. So make sure you save it. And you have to have this disk on your layer on your disk. Once you have this, let's click run. And now we have our final layer that we computed, which is our layer in EPSG 4326, which is the buffer zone around a metro station within 1 kilometer. And we don't need other layers at this point. So I'm going to select those. I can hold the shift key, select all layers I don't need, right click and remove them. So I only need the city boundary layer and this metro station buffer reprojected, which now both in 432. If you want to catch up to this point, you can load the checkpoint project open, geoprocessing checkpoint 2, which should look exactly like this, where we have our boundary and we have the buffer zone around metro station by 1 kilometer. And we are ready to do our final part of the analysis, where we can take this and compute the population that lives within this zone and compare it against the population that lives in the city. It's time for us to do our next challenge. So let's do our challenge 5.2.1. Vigna, you can explain the challenge.
So for the challenge, we want to find all the pubs which are within 1 kilometer of the metro station in the Bangalore city. Here we have this geo package which you can load in your QGIS, and after that you can look for the processing tool called select by location, and it will give you the option to select all the pubs within this buffer polygon that we have. So just you can use the data source manager to add the layer, and you can go to processing toolbox and say select by location and use this tool, your input, and you have to choose the intersect. So wherever the pub intersects buffer layer, it will be selected. So try this, configure it correctly, add the layer using this.
Let's move on. We have created this buffer zone. What all that is left for us to finish our analysis is to find out the population that lives within each of the zones. What is the population that lives in the city? What is the population that lives in this zone that we have created? How do you get data for population? Well, we need to get the data for population. There are many different sources, many different types. Let's learn a bit more about the options that we have. How do we get population data? Well, population data is typically derived from census data. Census data is collected and aggregated at, say, census blocks levels. So you have some polygon that was designed for census, and then you know the number of people that live there. And this is what you get. Now, this kind of vector-based population is useful if you just say, I want to get the population for the census blocks. But what if you have an arbitrary polygon? You say, I have this region, I want to count number of people. I can't use the census blocks starting point because I want to know exactly my zone might be only covering half of the census block. I don't want to know how many people live within that region of the census block. So for vector-based population dataset, you can't really know on an arbitrary region how many people live because we don't know the distribution of people within that polygon. So that's why for analysis, you typically use a raster-based population dataset. These are gridded population datasets where you take your data that typically comes from census, disaggregated on a grid. So you say, I will have a grid of 1 kilometer by 1 kilometer, I will take the census block data and disaggregate the data and assign some population to each grid of some regular size. And then we'll rasterize it and we distribute the data as raster. How the difference in all the data set that we're going to see is what is the algorithm for disaggregation. You say, I have this region, I know 1,000 people live there, but within this large polygon, where do they live? How do we assign people to different parts of that polygon? That is the key technique that differentiates most of the data sets. People use things like building counts, satellite imagery to say, I know in this region, half of the polygon that we have is all water body. Obviously, nobody can live there, so I'll assign more population to where there's land. Or people say, I will have building footprints, I'll figure out what type of building it is. If it's a high density living, I'll assign some people there and so on. So this is a kind of active area of research. People spend, the research groups that spend entirety of the time just figuring out techniques for doing this. And this forms the basis for many analysis. So getting accurate population count at grid level is a very important research topic. So once you do this, you will get a grid, a raster grid, where you have a pixel of 100 meter, 1 kilometer, whatever size you've chosen, and then you know the population count for that. And now we have the data, we can now say, I want to compute population in any given polygon, I can just count the number of pixels in that, and I can get the data. What are the good data set that you can use? We have a few options. NASA has a data called GPW, Gridded Population of the World. They have done this at 1 kilometer grid cell level. So you have 1 kilometer by 1 kilometer grid, and you have data available for this many years. So good data set to start with. There's another data set called GHSL. This is one of the most widely used, very high quality population data set. They have 250 meter grid cells, so pretty high resolution, especially at urban scales. 1 kilometer grid is 2 cores, because if your buffer zone is 1 kilometer and you miss a pixel, your population count will be off. So 1 kilometer pixel is 2 cores for many of the urban scale analysis. So GHSL is a good choice. They also have data for historic data as well as future data. So they have some projections as well as historic data. So till now, the GHSL is kind of the go-to choice for most researchers. If this fits your requirement, you should also consider using GHSL. Then there's WorldPop. This is Bill and Melinda Gates Foundation sponsored project, really high quality data set. They have 100 meter grid cells, and then they have yearly data. So it goes from 2000 all the way till 2020. I think they have a newer one as well now. So WorldPop is also very good, fine resolution and yearly data. So this is also a good choice. In my experience, for many regions that I evaluated, GHSL actually does a much better job, even though it's a little coarser than WorldPop. All of this really depends on the region that you're looking at. In some region, WorldPop is excellent because they have really good secondary data. In other regions, it's really bad. So since we have many choices, I urge you to get data from different providers, visually check, do some aggregation and validate whether this population count makes sense for the region that you're trying to analyze. There's a project by Facebook that took the WorldPop data and say, we will even refine it further based on satellite imagery. They got high-res satellite imagery for the entire world, and they took this 100-meter grid cell data, disaggregated it to a 30-meter grid cell. So the highest resolution population data is available to us at 30-meter grid cells, really good data, but the quality varies widely across the world. For Africa, this is really good. If you're doing any population analysis for Africa, I highly recommend this. I personally used it for a project where we used it for some analysis. We had teams on the field who validated our analysis, and it really matched really well. So again, the idea is you have this data freely available. Please make sure you evaluate it before you choose the one to use. For a lot of the research work, GHSL was the go-to data set. For commercial use, the data set that was widely used for a long time was Landscan. Landscan was a commercial data set, and many people who needed high quality commercial data, they would go and buy Landscan data. This was really high quality. In independent evaluation, it always showed up as the best data set, but it was a very expensive data set to buy. In recent times, some versions of Landscan have now become open source. So you have Landscan data also available to download for free, especially the Landscan Global, which is a 1 kilometer resolution data, which is available yearly from 2000 to 2022. If you are okay with the 1 kilometer grid scale, I would highly recommend using Landscan. If you want finer grain data, do evaluate GHSL and WorldPop for your region and pick the one that makes sense for you. So for the next step, we want to count the total population using this gridded population data sets. So when we load the data, you'll see a raster data. It looks like an image where each pixel will be having the count of people that are assigned to that pixel. So you say in this grid of 100 meter by 100 meter, we have 10 people or 50 people and so on. So we have the population count. We have the polygon of all the buffer zone, and we want to know how many people live there. We can overlay both and say, just give me the total pixels that are there. So all the pixels that fall within the polygon, we just sum up their values. And that will be the number of people that live within the polygon. This analysis is also known as zonal stats. Remember in our earlier presentation to join, if we have a polygon layer, we want to join it with a raster layer, the analysis that we want to do is zonal stats. So we have vector zones, and we can compute the sum of values from a raster using this tool. So let's go and implement this in QGIS. We are starting from our checkpoint 2 project. We want to load our raster data for next. So let's go to our data source manager, switch to the raster tab and browse to the data package and locate this file, Bangalore PPP 2020 constraint. This is the WorldPop population data for India that I had downloaded and then clipped it to the city of Bangalore. The entire data for India is very large. So I just clipped it to the polygon. When you download the data, you have two options to download. One is a constrained and unconstrained. A constrained data set means once you do the distribution of the data, your analysis says in this, they'll take some region, let's say a city, where they know the population count, and they say the population count says there are 1,000 people here. From our disaggregation in this city, our analysis says it's 1,100 people. So unconstrained will allow the population count to exceed the official population estimates. The constraint will say, no, we have to match our disaggregation to match the published population counts for different administrative region. So they will now adjust all of this accordingly. So this one is constrained. That means to take the whole city and count the sum of the pixels, it's going to match whatever is published as an official statistic. Depending on what you need, you can either take the constrained or unconstrained one. This one, we had downloaded the constrained one, clipped it to the city of Bangalore. So let's open that. And I'm going to click add. You see the raster data added into QGIS. The raster data is a grid of pixels. I can use the identify tool. So there's a tool in your toolbar called identify. You can use this and click on a pixel here. So if I click on a pixel, it's going to give me this value. It says in this pixel, the data set says there are 41.3 people. That's a population count. So the value of each pixel is the count number of people. There are some pixels with very high population, some pixels with very low population. So identify tool to query and look at the different regions. What we want to do is we have this different region. We can say, I have this buffer zone. I want to know how many people live in the buffer zone. So I can go and count all the values of all the pixels that fall within this buffer zone. And they'll give me all the people that live within 1 kilometer of a metro station. So let's do this analysis. We'll open the toolbox and we want to run the zonal stats by calculating the stats for this particular polygon. So once we have the Bangalore PPP raster layer loaded, let's search for the tool called zonal statistics. Double click to open it. We need to choose one vector layer and one raster layer. So the vector layer would be the buffer reprojected. The raster layer is the one we loaded. And this both have to match. So if they are in different projection, you will get null values. And that's the reason, remember in the last section, we had to reproject our final output to 4326. Since our raster data was in 4326, to be able to do this analysis, we had to reproject it. You could have kept it to 32643 and reprojected this raster layer, and that also could have worked. But remember, when you do analysis, both the projections have to match. A very common thing people often write to me, or I had a comment on my blog saying that, I did zonal stats and I get null values. And again, the reason would be projection mismatch. And that's why zonal stats won't work. We say the output column prefix, we're going to name it population. So change the prefix to be population underscore. So click these 3 dots. These are the different statistics that you can compute. So you have different pixels and you have different values. We want to compute different statistics. If we choose 3, for example, count, sum, and mean, you'll get 3 new columns, count, mean, sum, and mean in your vector layer. If you have a prefix, the column will be named population underscore count, population underscore sum, population underscore mean. If you don't have underscore, it'll be just population mean, population sum, etc. So it's just easy, it's just better to have an underscore so we can separate out different statistics. We just need the sum, so we can uncheck everything else. Let's just keep the sum, and we'll save our output to a file named metro station buffer pop. Once you configure this, go ahead and run this. This will take each polygon in our layer, compute the sum of pixels from this layer, and add a new column with an attribute named population underscore sum with the sum value. Get this new layer, metro station buffer pop. And now I can open the attribute table. And it shows me this count. This is the number of people that live in the buffer zone. If you're doing this analysis with the currently downloaded metro station data or at a later stage, you'll see a higher population because there are newer metro stations in the line. If you want to catch up to this point, you can load the checkpoint 3 project. This will be geoprocessing checkpoint 3, which now has this buffer pop layer with our answer on how many people live within the buffer zone. Let's do our next challenge where we know how many people live in the buffer zone. Let's compute how many people live in the whole city. What's the population count for the city? And then we can find out the percentage of people who live within 1 kilometer buffer zone. Vigna, you can explain the exercise.
So the challenge is to repeat the zonal statistic for Bangalore layer. So your input would be Bangalore. You were using the buffer layer earlier. So that would be your input, and you will use the same sum operator to get the population within the city. Now you have a count of people living within the city. Also, you have count for people living within 1 kilometer of the metro station. So you can use both these counts to get the percentage of people who are living within 1 kilometer of metro station. So try this exercise. You can repeat the same zonal statistic process with the different layer and get the count.
Once you had the new run the analysis, you'll get a new column, Bangalore or Bangalore pop sum. And then you can compare the two number and compute what's the percentage of people who live in the city who have access to the metro station within 1 kilometer of where they live. So we've done this analysis, population analysis, where we computed the buffer from metro station in a 1 kilometer zone. Let me load the metro stations. So for our analysis, we assume that if there's a metro station here, the people who live within a circular buffer distance of 1 kilometer can reach the metro station in 1 kilometer. That's not often true. You know that if you live, for example, here, you can't walk in a straight line to a metro station. What if there is no road and you have to take a longer route? So an actual analysis, if you want to do this, needs to take into account the road network into consideration and say, how many people can reach a metro station by walk or by car in 1 kilometer? Or even better, within some time frame. And that gives us a better analysis. So to do this, we can do something called network analysis. So I'm going to show you how we can improve this analysis by now accounting for the road network. So let's say you want to account for how many people can reach this metro station along a road network within 1 kilometer. And we have some really good data set available now globally, which is OpenStreetMap, which has got turn restrictions, speed limits, and all of those information available. We can use the OpenStreetMap network data to compute the actual buffers of certain distance. And these are known as isochrones. Isochrones are the regions where you can travel a certain distance and reach the zone. So we want to compute an isochrone and say, I want to use that as buffer zones. To do this in QGIS, we can use this plugin called Open Route Service. This is just a demo. You can do step by step later on if you need to. Which is a free service. It's a university project which takes the OpenStreetMap data, and they have a server which computes all the different analysis based on OpenStreetMap. They have a plugin which you can install. Once you install the plugin, You have to sign up on the website. It's a free service, but you have to go and obtain an API key. Once you obtain an API key, you'll have to go and enter the API key here. This is just to help abuse of the server, because it's an open server. You can overload the server with a lot of queries that limit the amount of traffic we can send to the server based on the API key. Once you have the API key, you will have a tool here once you install the plugin, and we can use this tool. You can do various types of network analysis. We're going to use this analysis isochrones from point layer. Just to demonstrate how this works, first I'm going to run this tool, isochrones from point. This will say we're using the open out service provider, how we want to use the service. So we can say, I want driving distance, walking distance, etc. If I say walk distance, it's going to respect the road restrictions. If there's a freeway and it says no pedestrians allowed, it won't keep you on that route. So again, depending on the network, you can use this. Let's just do, for example, driving distance. We'll pick an input point. Right now we're doing for one point, like this one. And we can either do time, how far you can drive for 10 minutes, or we can do a distance based. Let's do a distance based one. We'll say I want to know the buffer zone for 1 kilometer, 2 kilometer, and 5 kilometer. Okay, I'm going to do 3 zones. Let's run this. You don't need to download any data. The request goes to the server. The server computes those polygons along with the network, how far you can drive for 1 kilometer, 2 kilometers, and 5 kilometers. Let's see the result. You can see this is the 1 kilometer zone around this metro station. You can see it's not circular. If I compare this with my circular buffer, I can't live within a lake, right? This is a lake here. I can't live in the lake and still reach the metro station. I need to go around a route. Similarly, if there are turn restrictions, I can't reach there. So again, this is a much better representation of where you need to be to reach a metro station than that. And you can kind of go around. As you go further, you will see there are irregular polygons, not circular buffers. This will give you a much better indicator. So if you're doing any analysis, don't use circular buffers, use isochrones, which are more realistic, especially in an urban setting. I want to do this for all the points. I have multiple points. I'm going to now do walking distance. I'll say I want to know how far you can walk with 1 kilometer from the metro station. We can select some unique ID for just creating an output. And I'm going to do a 1 kilometer buffer, but this time along a network. Let's run this. As I'm running this, this service puts a restriction that you can only query 20 points per minute, just to make sure the server doesn't get overwhelmed. So after it does 20 points, it's going to stop and say, query limit reached. Please wait. Don't do anything. You can keep your tool running. It'll keep running for a few more minutes. Every minute it'll compute 20 isochrones, and then in 5 minutes you'll get your answer. So this doesn't cannot compute. It just said there is a restriction around that. I want to show you where those are listed. This is the website for the open route service. They have different plans. Everything is free. But if you are using your standard plan, it just says isochrones. Every day you can compute 500 isochrones. In a minute, you can only do 20. So if you have a lot of points, you have to wait for that. Again, this is without you doing any setup. You get a server free to use, and you get your data in QGIS. If you are doing this a lot, you can also install the software on your machine and run it with your OpenStreetMap data. So again, you can do this unlimited stuff. If you say, I want to do this a lot, I want to do it for thousands of points, you can install open route service using Docker on the machine and then run it the same tool, unlimited amount of time. For many people, this will be good enough. You can also download OpenStreetMap data, and then QGIS has built-in network analysis tools that you can use to compute that. No download, nothing. Just use the tool and you'll be able to do this. I'm going to cancel this for now. I have done this earlier today. I'm going to show you what the result of that looks like. So let me go and find this data. So these are the isochrones that were computed, 1 kilometer walking isochrones from each distance. And you can see this makes sense. For example, if you are here, this is a metro station here, and there's a river in between. You can't cross the river. You have to cross it at the road. You can't cross the river anyway. That's why you can see, if I live here, I cannot reach the metro station in 1 kilometer because I have to walk all the way here, cross this bridge, and then walk here. So this accounts for all the restrictions around the road network. And comparing with our buffer zone, you can see our circular buffer always overestimates the population that lives there. So a right way to do this would be to use isochrones as best fit for this kind of analysis. We have this thing called learning paths. This is exactly my answer to a question: how do we keep learning? I have learning paths for different software. So if you click on QGIS, this is the learning path I recommend. You've taken the introduction to QGIS course. Now it's a time to complete the advanced tutorials on the QGIS tutorials website. So you come here and you can say, I have advanced stuff I can do. If you can also do intermediate stuff, some of the stuff we have not covered yet in the basic stuff. So you can complete these tutorials. You'll learn things like, how do I do multiple maps? So I want to create a map book, one for each region. So I want to create 100 maps in a single operation. So I can set up your print layout so that I can do map automatically for different regions. You can do things like multi-criteria analysis. I have different layers. How do I figure out all the places which are near a river or away from a river, near a road, not in this region? How do I do this kind of analysis? So you have a lot of those kind of advanced techniques which are covered here. We have a whole bunch of YouTube videos, including the stuff that I mentioned about network analysis and other things. I also do a lot of talks in the QGIS events. I did some recently a podcast where I showed all the stuff that you never knew QGIS could do, like things like that. If you want to watch those, you can go and watch the videos and learn something new. Once you've done this, in 3 to 4 months' time, you're ready to do our advanced QGIS course. That will be a big eye-opener for many of you who've been using QGIS to now automate stuff. And this will be the kind of game changer for many people who now want to scale this analysis, use it in production. All of this is open source. I want to show you one more thing that will help you keep in touch with the QGIS community. There is a monthly event that is called QGIS Open Day. So this QGIS Open Day is a monthly event that happens on the last Friday of every month. It's live streamed on YouTube, where people would come in and even you as a user can come and propose a talk. People show stuff, how they're using QGIS, what's new in QGIS, and so on. There are talks. For example, earlier this year, somebody said, how to use QGIS with overture data. There's a new OpenStreetMap fork that has come in. You can meet people who are working on QGIS, live stream on YouTube. You can chat with people. The entire archive is also available. So past events with all the talks are also recorded and uploaded here. So you go and see there are talks that people have given. So it's a good way to kind of just connect with the QGIS community. Every last Friday of every month, just come to this page, log into YouTube, and you should be able to meet people and chat. It's generally a lot of fun. And I have also given talks, I think 4 or 5 times in the QGIS Open Day. So you can always fun to kind of meet everybody and connect with other QGIS users. So